Subscribe so you don't miss out on any of these videos. Imagine a star that has exhausted its nuclear fuel, met a violent end in a cataclysmic explosion, and yet, somehow, against all logic, refuses to die. It reignites, flickers back to life, and continues shining as if mocking the very forces that should have obliterated it. These are the so-called zombie stars, a mysterious class of celestial objects that challenge our understanding of stellar evolution, thermodynamics, and even the fundamental laws that govern space and time. For centuries, astronomers have observed stars in various stages of their life cycles. From their chaotic births and nebulae to their graceful demise as white dwarfs, neutron stars, or black holes, the story of a star's existence seemed well understood. But every so often, the universe throws a curveball, stars that explode in supernovae, only to inexplicably survive and begin shining again. These undead stars lurk in the cosmos, defying every known principle of astrophysics, leaving scientists baffled and rewriting textbooks in their wake. One such star, named IPTF-14HLS, was first spotted in 2014, and at first glance, it appeared to be a typical supernova, an explosion marking the violent death of a massive star. But as astronomers continued observing it, they noticed something utterly bizarre. Instead of fading away like every other supernova in recorded history, IPTF-14HLS refused to die. For years, it kept brightening and dimming as though it was undergoing multiple supernova explosions. This was unheard of. A supernova is a one-time event. A star explodes, and that's it, the end. But here was a star that had seemingly exploded multiple times, somehow defying the fundamental laws of physics. To make matters even stranger, historical records revealed that this same star had exploded before, in 1954. This meant that IPTF-14HLS had survived a supernova more than half a century earlier, only to explode again decades later. Nothing in our current understanding of stellar evolution can explain how this is possible. A supernova is supposed to be the grand finale of a star's life, a spectacular yet final act. But here was a star that refused to accept its fate. How is this possible? How can a star die more than once? Scientists have proposed several theories, yet none fully explain what's happening. One possibility is that IPTF-14HLS is a member of a rare and theoretical class of stars known as pulsational pair-instability supernovae. In this scenario, the star is so massive and hot that it begins producing antimatter in its core. This antimatter creation leads to runaway nuclear reactions that trigger massive eruptions, but not enough to destroy the star completely. Instead of one final explosion, the star undergoes multiple violent eruptions over time, shedding its outer layers while the core remains intact. This cycle could, in theory, allow a star to die multiple times before finally collapsing. But even this theory has problems. The amount of energy required for such a process is immense, and yet, IPTF-14HLS seems to have survived far longer than any model predicts. If this theory were correct, we would expect to see more examples of such stars in the universe, but so far, IPTF-14HLS remains an anomaly. Another theory suggests that the star could have been part of a binary system, meaning it had a companion star orbiting it. In this scenario, material from the exploded star could have been absorbed by its companion, reigniting fusion processes and creating the illusion of a star that refuses to die. However, this still wouldn't explain the multiple explosions seen in IPTF-14HLS, nor the historical record of its past supernova. Some scientists have even suggested exotic new physics could be at play. Could unknown quantum processes be allowing a star to reignite? Could dark matter or unknown forces be influencing the stellar core in ways we don't yet understand? The zombie stars of the universe seem to defy everything we thought we knew, opening up a frontier of mysteries that challenge the very fabric of astrophysics. Beyond IPTF-14HLS, there have been other cases of stars that seem to defy death. Some white dwarfs, the remnants of dead stars, have been observed reigniting under mysterious conditions. Others have shown unexpected bursts of energy, suggesting that the death of a star may not always be the end of the story. If these zombie stars truly exist, what does it mean for our understanding of the universe? Could there be stars out there that have survived multiple supernovae over billions of years? Could we be looking at a fundamentally new process that reshapes our understanding of stellar death? The deeper scientists look, the more questions arise, and with each discovery, the story of these undead stars only grows more perplexing. But this mystery goes even deeper. What if IPTF14HLS isn't an anomaly, but rather a glimpse into a hidden cosmic phenomenon we've simply never noticed before? The universe is vast, and our ability to observe it is still limited. Could there be countless other stars out there that have defied death in ways we've yet to understand? If so, what does this tell us about the very nature of energy, matter, and the life cycle of celestial objects? One of the biggest implications of zombie stars is what they could mean for the eventual fate of the universe. If stars can somehow survive their own deaths, does this hint at mechanisms that could allow energy to persist far longer than we assume? Could the heat death of the universe, the idea that everything will one day fade into darkness, be more complex than we thought? Could there be loopholes in entropy, the very law that dictates the inevitable decay of all things? These are the kinds of questions that make the zombie stars of the universe one of the greatest astrophysical enigmas of our time. Every new observation of these stars brings both answers and deeper mysteries. The more we uncover, the less we seem to understand. Yet, it is precisely these mysteries that drive science forward, pushing the boundaries of human knowledge into the unknown. Perhaps, in time, we will unlock the true nature of these undead stars. Perhaps we will discover that what we once thought was the end of a star's life is, in fact, just the beginning of an even stranger journey. Until then, the zombie stars remain one of the most haunting, mind-bending mysteries lurking in the depths of space, a riddle that refuses to be solved, just like the stars that refuse to die. As astronomers continue to investigate the mysteries of these zombie stars, they face an unsettling reality. Every explanation we currently have falls short. The case of IPTF14HLS remains the most compelling example, but the deeper scientists look into similar phenomena, the more they find that these undead stars are not isolated anomalies. They may represent an entirely new category of astrophysical events that we barely understand. Take, for instance, the enigmatic existence of white dwarf stars that seem to defy expectations. White dwarfs are supposed to be the final remnants of medium-sized stars like our Sun. Once they have burned through their nuclear fuel, they shrink into incredibly dense, Earth-sized objects, slowly cooling over billions of years. But some white dwarfs have been observed exhibiting bursts of energy, as if they are trying to reignite. This raises profound questions about whether stellar death is truly final, or if under the right conditions, stars can somehow cheat entropy and continue shining. One possible explanation for these outbursts is the process of accretion, in which a white dwarf steals material from a nearby companion star, temporarily reigniting nuclear fusion in its outer layers. However, this explanation only accounts for certain cases. It does not explain why some white dwarfs appear to flare up in the absence of any clear source of fuel. It also fails to account for stars like IPTF14HLS, which underwent multiple supernova-like explosions despite having no known stellar companion to feed it. Another perplexing case is that of supernova SN 2006 GY, which astronomers believe may have come from an extremely massive star that defied traditional stellar death. Unlike normal supernovae, which leave behind a neutron star or black hole, SN 2006 GY's explosion was so powerful that it seemed to destroy its progenitor completely. Yet, years later, unusual radiation patterns suggested that something might have survived. Did part of the star persist in some unknown form? Could there be a process we have yet to understand that allows remnants of dead stars to reform or sustain themselves against all odds? One of the biggest challenges in understanding these zombie stars is the sheer scale of time involved. The universe is nearly 14 billion years old, and stars live on timescales far longer than human civilizations. Even with our most advanced telescopes, we are only catching brief glimpses of these processes in action. A star that appears to reignite after a supernova could have taken decades, centuries, or even millennia to do so, meaning we are only witnessing a snapshot of a much longer and more complex process. This raises another unsettling possibility. what if our understanding of stellar death is fundamentally flawed? Could it be that stars do not simply follow a linear path from birth to death, but rather undergo cycles that we have yet to fully comprehend? Could some stars be trapped in an endless loop of death and rebirth, forever fluctuating between destruction and regeneration? There is also the question of exotic physics. Some scientists have speculated that unknown quantum effects could be at play, allowing matter and energy to persist in ways we do not yet understand. Others have suggested that dark matter, the mysterious, invisible substance that makes up most of the universe's mass, could be influencing these undead stars in ways we have yet to detect. If dark matter interacts with normal matter in unexpected ways, it could provide an unknown energy source that sustains stars long after they should have burned out. Another fringe but fascinating idea is the possibility of energy recycling on a cosmic scale. What if, instead of stars simply fading into nothingness, some of their energy is somehow trapped and later released in unpredictable bursts? This could explain why some white dwarfs seem to reignite, and why some supernova remnants produce inexplicable flashes of energy long after their supposed death. And then there is the question of black holes. If a star dies and collapses into a black hole, its energy is not truly lost, it is simply hidden behind the event horizon, where we can no longer observe it. But what if some of that energy finds a way to escape? Could zombie stars be linked to exotic processes occurring near black holes, where matter is constantly being drawn in and expelled in complex and poorly understood interactions? The implications of these mysteries extend far beyond just a handful of stars. If some stars can survive their own deaths, what does this mean for the ultimate fate of the universe? Many cosmologists believe that the universe will one day succumb to heat death, a state in which all energy is evenly distributed, and no useful work can be done. But if stars can cheat death, even temporarily, does this suggest that energy might persist in ways we have yet to understand? Could this hint at cycles of cosmic rebirth, where the universe itself undergoes periodic rejuvenation rather than a slow decay into nothingness? These questions go beyond astrophysics. They challenge the very foundations of thermodynamics, quantum mechanics, and cosmology. They force us to reconsider whether we truly understand the life cycle of the cosmos, or if we are only beginning to scratch the surface of a far deeper and more intricate reality. Perhaps the greatest mystery of all is whether these zombie stars are rare exceptions or if they are far more common than we realize. If our methods of observation are incomplete, we might be missing countless similar events scattered throughout the universe. With the next generation of telescopes, such as the James Webb Space Telescope and future gravitational wave detectors, we may finally begin to uncover the hidden secrets of these undead stars. For now, the zombie stars remain an enigma, a tantalizing mystery that suggests the universe still holds surprises far beyond our current understanding. They serve as a reminder that, despite all we have learned about space, we are still just beginning to unravel its deepest secrets. The more we search, the more questions we find. And as we peer deeper into the cosmos, we may discover that death, whether of stars, galaxies, or the universe itself, is not as final as we once believed. The existence of zombie stars challenges some of the most fundamental assumptions in astrophysics. For decades, scientists have relied on well-established models to explain how stars are born, live, and die. The process seemed clear. A star forms from a collapsing cloud of gas, ignites nuclear fusion in its core, burns for millions or billions of years, then either fades away or explodes in a spectacular supernova. But zombie stars defy this logic. They refuse to stay dead. They explode, yet somehow, they linger, sometimes reigniting, sometimes flickering back to life multiple times, as if they are caught in an endless cycle of destruction and rebirth. One of the strangest aspects of these stars is that they challenge the very definition of a supernova. A supernova, by definition, is supposed to mark the violent end of a massive star's life. In a Type II supernova, the core of the star collapses, triggering an immense explosion that blasts away the outer layers and leaves behind either a neutron star or a black hole. But in the case of IPTF-14 and similar objects, the explosion happens, yet the star refuses to disappear. Instead of collapsing into a neutron star or black hole, it seems to persist in an unstable state, flaring up multiple times over the course of years or even decades. This phenomenon has led scientists to question whether supernovae are as final as we once thought. Traditionally, supernovae were believed to be one-time events. Once a star explodes, its core either remains as a dense object or gets swallowed by its own gravity. But what if, under certain conditions, a star can resist total destruction? What if some stars are able to expel their outer layers in multiple stages, rather than in one single, cataclysmic explosion? One hypothesis that has gained traction is the idea that some supernovae are powered by what's called the pulsational parent stability mechanism. In this model, extremely massive stars, far larger than our Sun, reach a point where the intense radiation in their cores creates pairs of electrons and positrons. This process destabilizes the star, causing it to eject huge amounts of mass in multiple violent eruptions over time, rather than in a single explosion. This could explain why certain stars seem to undergo supernova-like events multiple times. Instead of completely disintegrating, they shed their outer layers in bursts, leaving behind a surviving core that continues burning for a time before eventually reaching its true end. However, even this explanation struggles to account for the most extreme cases of zombie stars. IPTF-14HLS, for example, showed at least 5 major outbursts over the course of several years, far more than what pulsational parent stability models predict. Some researchers have suggested that the star might have a dense, iron-rich core that repeatedly collapses and re-expands, generating multiple explosions over time. But this would require an unprecedented level of stability within the star's core, something that our current models do not account for. Another possibility is that these zombie stars are interacting with surrounding material in unexpected ways. When a star explodes, it often leaves behind a dense shell of ejected gas and dust. If the remaining stellar core somehow reignites, perhaps through magnetic interactions or residual nuclear burning, it could cause the surrounding material to light up again, creating the illusion of a star that refuses to die. This could explain some cases where stars appear to be flaring back to life long after they were thought to be dead. But this still does not fully explain stars that undergo multiple explosive events separated by years or decades. It also does not account for cases where the original stellar core seems to persist despite repeated outbursts. For this reason, some astronomers believe that an entirely new class of stellar objects may exist, one that does not fit neatly into our current categories of stars, supernovae, and remnants. Could it be that we are witnessing the birth of a new type of cosmic entity? Something neither fully alive nor fully dead, suspended between destruction and regeneration? If so, what does that mean for the life cycle of stars as a whole? If zombie stars are more common than we currently realize, it could have profound implications for our understanding of the universe. It could mean that stellar death is not as straightforward as we once believed. Instead of simply collapsing into a black hole or neutron star, some stars may experience prolonged, unpredictable phases of instability, during which they fluctuate between states of activity and dormancy. This could also mean that the night sky is filled with far more of these undead objects than we have been able to detect so far. The limitations of our observational technology also make it difficult to determine just how frequent these zombie stars are. Current telescopes and detection methods are designed to look for single, dramatic events, such as a one-time supernova explosion. But if some stars are undergoing prolonged cycles of activity, they may not fit neatly into our existing detection frameworks. They could be slipping under the radar, only becoming visible in rare instances when they flare up again after years of dormancy. This raises another fascinating question: could some of these zombie stars eventually return to a stable state and continue burning like normal stars again? If so, it would mean that stellar evolution is not as linear as we once thought. Some stars might be able to temporarily enter a death phase, only to reignite and continue shining for millions of years. Some researchers have even speculated that certain stars might be able to steal material from their surroundings in ways we do not yet fully understand. If a dying star is able to absorb gas and dust from nearby sources, it might be able to reignite its nuclear fusion process, effectively bringing itself back to life. This would require an unprecedented level of efficiency in how stars recycle material from their environment. However, if such a process does exist, it could change the way we think about how stars form, live, and die. There is also the question of whether these zombie stars could play a role in the formation of new stars. If a dying star sheds its outer layers repeatedly over time, it could be contributing to the creation of new nebulae, vast clouds of gas and dust that eventually give birth to new generations of stars. In this way, zombie stars could be acting as cosmic recyclers, ensuring that their material is reused in unexpected ways. The study of these stars is still in its early stages, and many more discoveries remain to be made. New observational tools, such as next-generation space telescopes and more powerful ground-based observatories, may finally allow us to uncover the full extent of this phenomenon. Future surveys of the night sky could reveal that zombie stars are far more common than we ever imagined, forcing us to rewrite the textbooks on stellar evolution. But even if zombie stars remain a rare anomaly, they still represent one of the most exciting and perplexing mysteries in modern astrophysics. They challenge our deepest assumptions about the nature of stellar life cycles, and they hint at processes that we have yet to fully understand. Ultimately, the existence of these undead stars serves as a reminder that the universe is still full of surprises. Despite centuries of astronomical research, we are still far from having a complete understanding of how stars live and die. The cosmos is vast, ancient, and complex, far more so than we have ever imagined. And as we continue to explore its depths, we may find that even death itself is not as final as it seems. If zombie stars truly exist as a recurring phenomenon rather than an anomaly, it forces us to rethink not only the death of stars but also the very nature of energy persistence in extreme astrophysical environments. One of the most baffling aspects of these undead stars is their ability to sustain luminosity for years after an explosion that should have depleted their energy entirely. Traditional supernova models suggest that once a star reaches the end of its life, its fuel runs out, leading to an inevitable collapse or detonation. But these zombie stars seem to find a way to persist, either by reigniting, feeding off external material, or existing in a semi-dormant state where they remain in flux between death and rebirth. One of the leading theories trying to make sense of this phenomenon involves Magnetars, neutron stars with incredibly powerful magnetic fields. When a massive star explodes, its core can collapse into a neutron star, a dense remnant that holds more mass than the Sun but is packed into an object only a few kilometers wide. If this neutron star also possesses an extremely strong magnetic field, it can influence its surroundings in unexpected ways. Some astrophysicists believe that magnetars could be responsible for some cases of zombie stars, as their powerful magnetic fields could delay or even alter the normal decay process after a supernova explosion. Instead of fading into obscurity, the dying star might experience magnetic interactions that generate enough energy to reignite bursts of luminosity. Another possibility is that some zombie stars are the result of an extreme type of binary interaction. Many stars exist in binary systems, where two stars orbit each other. If one of these stars undergoes a supernova but does not completely destroy itself, it could begin to siphon material from its companion, effectively stealing mass and reigniting in a way that appears as if the star is returning from the dead. In some cases, this could even lead to a delayed explosion, where the undead star eventually gathers enough material to undergo another supernova event. A particularly intriguing case of such a scenario is seen in Type IX supernovae, which are sometimes called zombie star supernovae, because they do not fully destroy the progenitor star. Unlike normal Type I supernovae, which completely obliterate their white dwarf progenitor, Type IX events leave behind remnants, dense stellar cores that refuse to die. Some of these remnants continue burning at low levels, while others appear to reignite, flaring up multiple times over decades. This suggests that some stars are not completely destroyed by their own supernovae but instead remain in a bizarre, lingering state of existence. Even more puzzling are cases where zombie stars appear to undergo multiple eruptions, spaced out over years. This is what makes IPTF-14HLS so fascinating. It did not simply flare up once, but rather experienced at least 5 distinct outbursts, something completely unexpected in the life cycle of a supernova remnant. The persistence of this behavior suggests that some kind of internal mechanism is regulating these explosions, rather than a single catastrophic event marking the end of the star's existence. If zombie stars can indeed survive supernovae and continue burning in some form, it raises an even more fundamental question: what defines a star's death? Traditionally, a star is considered dead when it can no longer sustain nuclear fusion. But if a star is able to reignite through external interactions or internal mechanisms, can we truly say it ever died in the first place? Could some stars cycle between active and inactive states over cosmic timescales, challenging our very definitions of stellar life and death? This also ties into the idea that the universe may be far more dynamic than we have previously assumed. We often think of stellar evolution as a straightforward sequence: birth, main sequence, red giant phase, and then eventual death through supernova or slow cooling. But what if this process is not always linear? If zombie stars exist, they could represent an entirely new phase of stellar evolution, one that involves multiple cycles of collapse, explosion, and revival. Moreover, the implications extend beyond stars themselves. If energy can persist in ways we do not yet fully understand, it could have profound consequences for our understanding of cosmic processes as a whole. The persistence of these undead stars suggests that energy transfer mechanisms in space may be more complex than we currently model. If stars can temporarily cheat death, is it possible that other celestial objects, such as neutron stars or even black holes, could exhibit similar behavior under the right conditions? Perhaps some of the most exciting possibilities come from the idea that zombie stars could serve as laboratories for new physics. If we can study how these objects continue to emit light and energy despite undergoing supernovae, we may uncover hidden principles of matter, magnetism, or even exotic forms of fusion that do not conform to current theories. Could there be unknown reactions occurring in these undead stars that allow them to persist beyond their expected lifespans? Are there forces at play that we have yet to detect, influencing how stars interact with their environment long after their supposed death? To explore these mysteries, astronomers are developing new observational techniques that could allow us to catch more of these zombie stars in action. Large-scale sky surveys, such as those conducted by the Vera C. Rubin Observatory, are designed to scan the sky repeatedly over time, searching for objects that change unexpectedly. If zombie stars flare up multiple times, future telescopes may be able to track their entire life cycles, helping us understand exactly what drives their continued existence. But even with the most advanced telescopes, zombie stars remain one of the most elusive mysteries in astrophysics. Their unpredictable nature makes them difficult to study, as they do not follow the expected patterns of traditional supernovae. Some might remain dormant for decades or even centuries before suddenly reigniting, making them almost impossible to detect unless astronomers are looking in precisely the right place at the right time. Even more mind-bending is the idea that some of these zombie stars might not be unique at all, but rather part of a much larger population that has gone unnoticed. If stars can survive explosions more frequently than we assumed, then the remnants of countless supernovae could still be burning in hidden corners of the universe, masquerading as ordinary stars or dim, flickering objects that evade detection. Ultimately, the study of zombie stars is not just about understanding how some stars refuse to die. It is about challenging our most fundamental assumptions about the cosmos. If stars can persist beyond their expected lifespans, it suggests that the universe itself may be full of unknown processes, cycles, and interactions that we have yet to fully comprehend. Perhaps one day, with more advanced telescopes and deeper theoretical insights, we will finally unravel the mystery of these undead celestial objects. But until then, the universe will continue to surprise us, reminding us that even in the depths of space, death may not always be the end. The implications of zombie stars stretch far beyond their own strange existence. If these stars can survive what should be a final, catastrophic explosion, then what else in the universe might endure beyond what we currently predict? Could other celestial objects, perhaps even entire planetary systems, persist in ways we never expected? The discovery of zombie stars may be just the beginning of a larger realization that cosmic death may not be as absolute as we once believed. One of the most striking aspects of this phenomenon is how it challenges our understanding of thermodynamics in extreme astrophysical conditions. A supernova should represent the final dissipation of energy, a one-way conversion of matter into an explosive release of radiation and particles. Yet, if zombie stars continue to shine, it suggests that energy can be stored, delayed, or even re-triggered in ways that are not fully explained by standard models. Could there be unknown forms of energy retention at play, perhaps linked to exotic states of matter? One of the leading hypotheses for how zombie stars persist is the role of dark matter. Dark matter is one of the greatest unsolved mysteries in astrophysics. It makes up the majority of the universe's mass, yet it does not emit or absorb light, making it nearly impossible to detect directly. Some scientists speculate that zombie stars could be interacting with dark matter in ways we have yet to understand. If these stars are embedded in regions of high dark matter density, it is possible that dark matter particles could be annihilating within them, releasing bursts of energy that temporarily revive the stars. Another potential explanation lies in quantum effects that might operate at astronomical scales. Quantum mechanics describes bizarre behaviors at microscopic levels, such as particles existing in multiple states simultaneously. While quantum effects are usually limited to subatomic interactions, some researchers wonder if extreme environments like supernova remnants could magnify these effects. Could quantum tunneling or other unknown quantum processes be enabling energy to persist within the remnants of exploded stars? Could some form of quantum instability be responsible for the periodic flare-ups of zombie stars, allowing them to jump between energy states in ways we do not yet understand? Additionally, the very composition of these stars could hold secrets to their persistence. Stars that go supernova are typically composed of heavy elements forged through nuclear fusion over millions or billions of years. However, recent studies suggest that certain types of supernovae may leave behind exotic forms of matter, such as quark-gluon plasma, a state of matter that existed in the early universe, where protons and neutrons break down into their fundamental components. If zombie stars contain pockets of this extreme material, they may possess unique properties that allow them to reignite under the right conditions. Some theories even suggest that zombie stars could be acting as natural particle accelerators. The intense magnetic fields generated by their remnants could create conditions similar to those found in man-made accelerators like the Large Hadron Collider. If these fields are strong enough, they might be capable of accelerating particles to nearly the speed of light, generating bursts of high-energy radiation that could be mistaken for a star reigniting. This would mean that what appears to be a living star may, in fact, be a cosmic laboratory for high-energy physics, producing phenomena that could help us unlock new laws of nature. Perhaps the most mind-bending possibility of all is that zombie stars hint at unknown dimensions of time. Our current models of physics treat time as a linear progression, but certain interpretations of relativity suggest that time may be more flexible than we think. Some theorists speculate that zombie stars could be experiencing localized time dilation effects, where time moves differently within their remnants than it does in the rest of the universe. If time flows differently inside the cores of these stars, their apparent resurrections might not be a true revival, but rather the result of an altered passage of time that allows them to appear active long after they should have faded away. If this is true, then the discovery of zombie stars might provide one of the first hints that time itself is not as uniform as we assume. Could certain regions of space experience altered flows of time? If so, are there other objects, perhaps even entire galaxies, that exist in time frames different from our own, appearing dead when they are actually still active? Or vice versa? The implications of this would be staggering, as it could redefine our very perception of cosmic history. To truly understand zombie stars, astronomers are now focusing on identifying more of them across the universe. Large-scale sky surveys and space-based observatories are scanning distant galaxies, looking for any signs of stars that have flared up unexpectedly. If zombie stars are more common than we think, they could revolutionize our understanding of stellar evolution and cosmic energy cycles. Future space telescopes, such as the James Webb Space Telescope and the upcoming European Extremely Large Telescope, may provide new insights by capturing detailed images and spectra of suspected zombie stars. By analyzing their chemical compositions, temperatures, and energy emissions, scientists hope to determine what makes these stars unique and why they continue to persist when all logic suggests they should be gone. The most exciting part of this mystery is that we are only beginning to scratch the surface. The existence of zombie stars challenges everything we thought we knew about the life cycles of stars, energy conservation, and even the nature of time and space itself. If we can unravel the secrets of these undead celestial objects, we may unlock new physics that could transform our understanding of the universe in ways we cannot yet imagine. The search for zombie stars is more than just an astrophysical curiosity. It is a glimpse into the unknown, a reminder that the universe is full of surprises waiting to be uncovered. And as we continue to look deeper into the cosmos, one thing is certain: the story of the stars is far from over. The existence of zombie stars forces us to reconsider fundamental assumptions about stellar life cycles, energy persistence, and even the nature of cosmic evolution itself. If stars can somehow survive their own death, what does this mean for our broader understanding of the universe? Could it be that other astronomical objects, planets, neutron stars, or even entire galaxies, possess similarly hidden mechanisms of renewal? The mystery of zombie stars may be just one piece of a larger cosmic puzzle, one that challenges our deepest held beliefs about the finality of destruction in the cosmos. One of the biggest open questions surrounding zombie stars is whether they are truly rare or if we have simply failed to notice them in the past. Historically, astronomers have classified stars and their life cycles based on broad observational patterns. When a supernova occurs, we assume it marks the end of that star's activity. But what if many supernovae actually leave behind stellar remnants that persist in unexpected ways? What if zombie stars are a relatively common but overlooked phenomenon, hidden within the noise of our astronomical data? The discovery of IPTF-14HLS, a star that exploded multiple times over several years, was a complete accident. No one was actively looking for such a phenomenon because it was not supposed to exist. This raises an intriguing possibility. If astronomers were to systematically search for similar cases, how many more might they find? Some researchers speculate that zombie stars might explain other strange, long-duration supernova-like events that have been observed in the past but dismissed as anomalies. One method for uncovering these hidden undead stars is through deep space time-lapse surveys. By repeatedly scanning the same regions of the sky over long periods, telescopes can detect changes that would otherwise go unnoticed. If a star that supposedly exploded decades ago suddenly flares up again, it would provide strong evidence that zombie stars are more than just a rare curiosity. This type of research is still in its infancy, but technological advancements are making it increasingly feasible. The Vera C. Rubin Observatory, set to begin full operations in the near future, is designed to conduct precisely this kind of long-term sky monitoring. It will capture vast amounts of data on changing celestial objects, potentially revealing whether zombie stars are a fluke or a widespread cosmic mystery. Another key avenue of research involves studying the remnants of known supernovae. Some supernovae leave behind neutron stars, while others collapse into black holes. But what if some leave behind a third, as yet unidentified type of object, one that retains enough energy to intermittently flare back to life? Future missions like NASA's James Webb Space Telescope and the European Space Agency's Athena X-ray Observatory may help answer this question by closely examining supernova remnants for signs of unexpected activity. One of the most tantalizing aspects of zombie stars is their potential connection to other extreme cosmic phenomena. Some astrophysicists suspect that these objects might be linked to fast radio bursts, FRBs, mysterious, extremely powerful flashes of radio waves that originate from deep space. While many FRBs are one-time events, some have been observed repeating, suggesting that their sources are not being destroyed. Could it be that certain zombie stars, perhaps those with ultra-strong magnetic fields, are the origin of these strange bursts of energy? If so, studying them could help solve two astrophysical mysteries at once. Another possible connection lies in the enigmatic nature of long-duration gamma-ray bursts, GRBs. Typically, GRBs are associated with the collapse of massive stars or the merger of neutron stars, leading to a powerful outpouring of energy. But some gamma-ray bursts last much longer than expected, with energy emissions continuing for hours or even days. If zombie stars can undergo multiple explosive events, they could be responsible for some of these unusually prolonged bursts of radiation. Beyond these observational challenges, the discovery of zombie stars raises profound theoretical questions about the very nature of matter, energy, and time. If a star can remain active long after it should have burned out, does this suggest that energy can be stored or recycled in ways we do not yet understand? Could these objects harbor unknown physical mechanisms that allow them to cheat death? One particularly radical hypothesis is that zombie stars might be tapping into hidden energy sources within the universe. Some speculative theories suggest that the vacuum of space itself may contain vast reservoirs of energy, what physicists call vacuum energy or zero-point energy. If zombie stars have some way of accessing this hidden energy, it could explain how they continue to shine long after they should have faded. This would have staggering implications not just for astrophysics, but for our understanding of energy itself. Another mind-bending idea is that these undead stars might be experiencing nonlinear time effects. General relativity predicts that strong gravitational fields can warp time, slowing it down or even distorting it entirely. If zombie stars exist in regions of extreme gravitational influence, perhaps near black holes or in dense star clusters, could their apparent longevity be an illusion caused by time dilation? If time flows differently within these objects, what seems like a star repeatedly reigniting over years or centuries might, from its own perspective, be occurring in a much shorter time span. As we continue to investigate zombie stars, we may also gain insights into one of the biggest unsolved questions in physics: the true nature of dark energy. Dark energy is the mysterious force driving the accelerated expansion of the universe, yet its origin and mechanism remain unknown. Some researchers speculate that extreme astrophysical objects, such as magnetars, neutron stars, or even zombie stars, might hold clues to how dark energy operates on cosmic scales. If these undead stars interact with space-time in an unusual way, they could provide indirect evidence for new physics governing the structure of the cosmos. Ultimately, the study of zombie stars is not just about understanding an unusual stellar anomaly. It is about challenging the very boundaries of what we think is possible. These stars defy established models of stellar evolution, suggesting that our current understanding is incomplete. They force us to ask deeper questions about the nature of cosmic death, the persistence of energy, and whether the universe itself might be capable of recycling matter and energy in ways we do not yet comprehend. The more we investigate these objects, the more questions arise. Could some zombie stars be in the process of evolving into entirely new types of celestial bodies? Are they remnants of previous cosmic cycles, hinting at an eternal universe where nothing truly dies? Could their strange behavior be the key to unlocking hidden forces that shape the very fabric of reality? As our telescopes grow more powerful and our theories more refined, we may one day find definitive answers to these questions. But until then, the mystery of the zombie stars remains one of the most intriguing and perplexing enigmas in modern astrophysics. They serve as a stark reminder that the universe is far from fully understood, and that even in the vast emptiness of space, death may not be the end. If zombie stars truly defy conventional astrophysical models, what does that say about the broader nature of stellar evolution? For decades, astronomers have mapped out the life cycles of stars with remarkable precision. A star is born from a collapsing cloud of gas and dust, fuses hydrogen into helium in its core for millions or billions of years, then either fades away peacefully or meets a dramatic end in a supernova. But the existence of zombie stars suggests that this narrative is incomplete. Could it be that there are unknown pathways in stellar evolution, alternative routes that allow certain stars to resist their fate? One possibility is that some stars harbor hidden reservoirs of energy that allow them to reignite after a supernova. We typically assume that when a star explodes, its outer layers are ejected into space while its core collapses into a neutron star or black hole. However, if some stars have an internal structure that allows energy to be trapped and later released, they might be capable of multiple explosions. This would make zombie stars fundamentally different from other stellar remnants. Rather than being entirely dead, they might exist in a suspended state, fluctuating between dormancy and revival. Some astronomers speculate that the key to understanding zombie stars lies in their composition. Most stars are made primarily of hydrogen and helium, with heavier elements forming in their cores over time. However, if a star contained unusual ratios of exotic elements, such as large amounts of carbon, oxygen, or even antimatter, it could potentially undergo cycles of explosive reignition. The presence of antimatter, in particular, could lead to periodic energy releases, as matter and antimatter annihilate each other in bursts of radiation. If this process occurs deep within a star's core, it might explain the periodic flaring seen in some zombie stars. Beyond their composition, the physical environments surrounding zombie stars might also play a role in their behavior. Some exist in binary systems, orbiting closely with another star. If a zombie star is locked in a gravitational dance with a companion, it could periodically siphon material from its partner, triggering new nuclear reactions. This type of interaction, known as accretion, is already observed in white dwarfs that undergo nova eruptions. But in the case of zombie stars, the process might be more extreme, leading to full-fledged supernova-like events that repeat over time. Another theory suggests that zombie stars might be linked to Magnetars, a rare type of neutron star with extraordinarily strong magnetic fields. Magnetars are known to emit powerful bursts of X-rays and gamma rays, and their extreme magnetic forces can twist and deform their surfaces, sometimes triggering explosive outbursts. If some supernova remnants evolve into magnetars instead of traditional neutron stars, they might retain the ability to reignite under the right conditions. This could explain why some zombie stars appear to explode multiple times over the course of years or even centuries. But what if the explanation for zombie stars goes beyond traditional astrophysics? Some researchers have proposed that these objects might be connected to exotic particles or even extra dimensions. According to certain extensions of string theory, the universe may contain hidden spatial dimensions beyond the three we perceive. If zombie stars interact with these dimensions in some way, perhaps by funneling energy into or out of them, they could behave in ways that defy normal physics. One speculative idea is that zombie stars might act as natural portals between different regions of space-time. If energy is somehow leaking into them from another part of the universe, it could explain why they seem to reignite long after their expected death. This would have profound implications not just for astrophysics, but for our understanding of the very structure of reality. Could it be that these stars are drawing power from a hidden cosmic reservoir, sustaining themselves through unknown means? Even more radical is the idea that zombie stars might be tied to violations of the second law of thermodynamics, the principle that states energy always flows from order to disorder. In most natural systems, once energy is dispersed, it cannot be fully recovered. However, if zombie stars are able to spontaneously reignite, it suggests that some process is reversing entropy on a local scale. This would be an extraordinary discovery, hinting at new physics that could redefine our understanding of energy conservation. One possible mechanism for this involves vacuum fluctuations, quantum-level distortions in empty space that generate brief bursts of energy. In most cases, these fluctuations are tiny and cancel out, but if zombie stars are somehow amplifying them, they could be tapping into a previously unrecognized energy source. This would make them the first known macroscopic objects to harness quantum energy on a cosmic scale. The discovery of zombie stars also raises profound philosophical questions about the nature of cosmic death. If stars can survive what should be a final, destructive explosion, does this mean that other cosmic phenomena might also persist beyond their apparent end? Could black holes, for instance, undergo a similar form of resurrection, re-emerging as new celestial objects after billions of years? Could entire galaxies be capable of periodic rebirths, cycling through phases of destruction and renewal? If this turns out to be the case, then the universe itself might be far more dynamic than we currently assume. Rather than a place where objects live, die, and fade into obscurity, the cosmos could be a realm of perpetual transformation, where destruction is never truly final. This would lend support to theories suggesting that the universe might undergo cycles of expansion and collapse, with stars, planets, and galaxies continuously emerging and dissolving over cosmic timescales. The implications for space exploration are equally fascinating. If zombie stars represent a new class of celestial object with unknown energy generation mechanisms, they could serve as natural laboratories for studying exotic physics. Future spacecraft equipped with advanced sensors might be able to probe these stars directly, gathering data on their energy output, magnetic fields, and particle emissions. If we can unlock the secrets of their resilience, it could lead to breakthroughs in energy production, spacecraft propulsion, and even interstellar travel. Some visionaries have even speculated that if zombie stars are tapping into hidden energy sources, they might serve as potential weapons for future civilizations. If humanity, or an advanced alien species, could learn to harness the same processes that allow these stars to reignite, it might enable the development of new energy technologies capable of sustaining deep space exploration. Could the study of zombie stars eventually lead us to a method for generating limitless, self-renewing power? As scientists continue to investigate these enigmatic objects, one thing is clear: zombie stars challenge our fundamental understanding of how the universe works. They defy the expectations of astrophysics, hint at hidden forces we have yet to comprehend, and suggest that the boundaries between life and death in the cosmos are far more fluid than we ever imagined. The more we learn about zombie stars, the more we are forced to confront the vast unknowns that still exist in our understanding of the universe. They remind us that even in the depths of space, where we assume silence and stillness, there are phenomena waiting to surprise us, phenomena that could reshape our understanding of reality itself. And so, the search continues. Astronomers will keep scanning the heavens, searching for more examples of these undead stars, hoping to unravel their mysteries. Perhaps the next great breakthrough in astrophysics will come not from studying black holes or dark matter, but from understanding why some stars refuse to die. The mystery of zombie stars remains one of the most perplexing enigmas in astrophysics, forcing scientists to reconsider everything they thought they knew about stellar evolution, energy conservation, and the very structure of the universe itself. These stars, which defy death and seemingly regenerate after catastrophic explosions, challenge the traditional understanding of how matter and energy behave on a cosmic scale. What keeps them alive? How do they reignite after what should have been their final moments? And most importantly, what does this mean for our broader understanding of space and time? One possible explanation, though still speculative, involves the concept of delayed nuclear fusion. Under normal circumstances, when a star explodes in a supernova, the nuclear fusion process that once powered it comes to an abrupt halt. The core either collapses into a neutron star or black hole, while the outer layers are ejected into space in a brilliant display of energy. But what if some zombie stars contain elements or conditions that allow nuclear reactions to persist long after the explosion? There's growing speculation that some of these stars might undergo partial explosions rather than complete ones. In this scenario, only part of the star's mass is blown away, while a significant portion of its core remains intact. If the right conditions are present, such as intense gravitational compression, an influx of fresh hydrogen from a nearby star, or an unusual magnetic configuration, nuclear fusion could restart, giving the appearance of a star resurrecting itself from the dead. A particularly strange class of zombie stars includes those that have undergone multiple supernova-like events over the course of decades or centuries. One of the most famous examples is IPTF-14HLS, a star that exploded in 1954, only to seemingly explode again in 2014. Traditional models of stellar death suggest that a star cannot survive one supernova, let alone multiple. Yet, IPTF-14HLS remains, defying explanation. What force is allowing it to experience multiple death throes while continuing to shine? Some theories propose that IPTF-14HLS and similar stars may be examples of pulsational parinstability supernovae. In these rare cases, the immense heat and pressure in a massive star's core can cause gamma rays to convert into particle-antiparticle pairs. This process momentarily robs the star of radiation pressure, causing it to partially collapse before rebounding in a violent explosion. But rather than destroying the star completely, the explosion sheds only its outer layers, leaving the core intact. This cycle can repeat multiple times, leading to a series of supernova-like outbursts over decades or even centuries. But even pulsational pair instability doesn't fully explain all zombie stars. Some seem to reignite in ways that cannot be accounted for by known fusion processes. Could something else be at play? Some researchers have suggested that zombie stars might be tapping into a hidden energy source, possibly linked to dark matter or even exotic physics beyond the standard model. Dark matter is one of the most mysterious substances in the universe, comprising an estimated 85% of all matter. Though it does not emit, absorb, or reflect light, its gravitational effects can be observed on large cosmic structures. What if some zombie stars are somehow interacting with dark matter in a way that allows them to draw energy from it? If dark matter particles have a mechanism for self-annihilation, as some theories suggest, they could provide a hidden energy reservoir that allows certain stars to continue shining long after they should have burned out. An even more exotic idea is that zombie stars could be linked to primordial black holes, tiny black holes that may have formed in the early universe. If a small primordial black hole were trapped inside a massive star before its supernova, it could periodically feed on the star's remaining material, releasing bursts of energy that mimic stellar revival. This would create the illusion of a star that refuses to die, even though the true source of its energy is a hidden black hole consuming its remains from within. Some scientists have even speculated that zombie stars could be related to cosmic strings, hypothetical, ultra-thin defects in the fabric of space-time that may have formed during the early universe. If a cosmic string were to pass through or become entangled with a dying star, it might generate intense bursts of energy, triggering new explosions and creating the appearance of a star coming back to life. Though purely theoretical, this idea highlights how zombie stars could be linked to unknown physics that extend far beyond traditional stellar models. What makes these stars even more baffling is the sheer variety of ways they seem to cheat death. Some appear to reignite from their own material, while others seem to gain fresh fuel from their environment. Some experience multiple explosive outbursts over time, while others appear to flicker back to life long after being presumed dead. This diversity suggests that zombie stars may not be a single phenomenon but rather a collection of different stellar anomalies that all share the common trait of defying expectations. The implications of this mystery stretch far beyond astrophysics. If zombie stars are powered by unknown forces or hidden cosmic mechanisms, it could mean that other objects in the universe, planets, galaxies, even black holes, might also experience forms of renewal we do not yet understand. Could it be that the cosmos itself operates on cycles of death and rebirth at scales we have not yet grasped? Could there be hidden rules of energy transfer or cosmic recycling that allow matter to persist in ways we never imagined? One of the most profound questions that zombie stars raise is whether death, as we understand it, is ever truly final. In human terms, we often think of life and death as binary states. Something is either alive or dead, active or extinct. But in the cosmos, the boundaries are not always so clear. Stars that should be gone continue to shine. Objects that should have collapsed into darkness re-emerge in unexpected ways. The universe, it seems, has ways of preserving and renewing itself that we are only beginning to understand. The more we study these stellar anomalies, the more we are forced to confront the possibility that we are missing fundamental pieces of the cosmic puzzle. Could the laws of thermodynamics, as we currently understand them, be incomplete? Are there hidden dimensions of energy flow in the universe that we have yet to detect? What other surprises await us in the vast, uncharted depths of space? As telescopes become more advanced and space observatories scan the universe with ever-increasing precision, we may soon uncover more examples of zombie stars. Perhaps we will find an underlying pattern that explains their behavior, or perhaps they will continue to confound us, remaining as ghostly reminders that the universe is far stranger than we ever imagined. One thing is certain: zombie stars refuse to be ignored. Their very existence is a challenge to our understanding of reality, a riddle that demands answers. Whether they are powered by hidden fusion processes, dark matter interactions, exotic physics, or something even more mysterious, they stand as cosmic anomalies that remind us just how much we still have to learn about the nature of existence. And so, the search for answers continues. Astronomers will keep watching the sky, tracking these undead stars, and looking for clues to their impossible survival. Perhaps, in unraveling the mystery of zombie stars, we will unlock secrets not just about the universe, but about the very fabric of reality itself. As astronomers continue their relentless quest to understand zombie stars, new discoveries may rewrite our understanding of stellar physics and the fate of dying stars. Every new observation, every anomalous light curve, and every unexplainable stellar explosion pushes the boundaries of what we thought was possible in the universe. One of the most astonishing aspects of zombie stars is their ability to defy time itself. In our understanding of astrophysics, stellar lifetimes follow well-defined paths. Massive stars burn through their fuel in a predictable sequence, ending in a supernova that marks their ultimate fate. However, zombie stars disrupt this expected progression, behaving as though they exist outside the conventional timeline of stellar evolution. For example, take IPTF-14HLS, the supernova that exploded not once but multiple times over several decades. When scientists first discovered it, they assumed it was a typical Type 2P supernova, a common stellar explosion from a massive star. However, as they continued observing, they noticed something strange. It wasn't fading as expected. Instead of dimming over the usual few months, it remained bright for years. Even more perplexing, when historical astronomical data was examined, researchers found that the same star had apparently exploded back in 1954. How could this be? The most puzzling part is that the explosion didn't behave like any known supernova. Most supernovae reach peak brightness, and then fade predictably as their radioactive decay slows down. But IPTF-14HLS fluctuated in brightness, experiencing multiple peaks over the course of years. This suggested that whatever was happening inside the star was not a one-time event. It was undergoing continuous energy releases in ways astrophysicists had never seen before. One explanation proposed by scientists is the possibility that these stars are so massive that their internal physics operate in a way never before observed. Some models suggest that the extreme mass of these stars allows them to undergo pulsational pair instability, where the star doesn't fully explode but instead experiences repeated violent ejections of its outer layers. These partial explosions can cause the star to appear as if it is dying multiple times before it finally collapses into a black hole. But even this model doesn't fully explain all zombie star behavior. In some cases, stars that should have completely disappeared are instead reigniting and burning brightly again. This raises questions about how these objects are regaining energy. Could external factors be fueling them? Could they be pulling material from surrounding gas clouds, reigniting fusion in the process? Or is there an entirely new type of physics at play, one that allows for stellar resurrection in ways we don't yet understand? One possibility is that some of these stars exist in binary systems, where a close companion star provides new material to the zombie star after it has exploded. If the zombie star is a partially collapsed remnant, it could steal hydrogen or helium from its companion, slowly reigniting fusion at its surface. This could explain some instances of stars that seem to come back to life long after they should have burned out. However, not all zombie stars have nearby companions. Some are isolated, far from any apparent source of new fuel. In these cases, scientists are left wondering, where is the energy coming from? Some researchers have proposed that these objects might be tapping into exotic forms of energy, possibly from interactions with dark matter. Dark matter is a mysterious substance that makes up most of the universe's mass, but has never been directly observed. If some stars have a way of interacting with dark matter in a way that produces energy, it could provide a hidden power source that allows them to persist long beyond their expected lifespans. Another theory suggests that some zombie stars could be involved in quantum-scale phenomena that allow energy to be stored and released in ways we do not yet understand. In physics, there are cases where energy can be temporarily trapped in metastable states before being suddenly released. If a similar principle exists at the scale of massive stars, it could mean that certain stellar explosions are not final, but rather phases in a longer, more complex process. There is also speculation that some zombie stars could be connected to white dwarfs that undergo a process known as reignition. White dwarfs are the remnants of low to medium mass stars that have exhausted their fuel, typically fading into dim, cold embers over billions of years. However, under the right conditions, some white dwarfs can accumulate enough material to undergo a new burst of fusion, creating a phenomenon known as a born-again star. If similar processes are occurring on a much larger scale in high-mass stars, it could help explain why some supernovae seem to produce stars that refuse to die. Some scientists have even proposed that zombie stars might be evidence of completely new physics, laws of nature that we have not yet discovered. The universe is vast and full of mysteries, and our understanding of matter, energy, and time is still evolving. It is possible that the way we think about stellar life cycles is incomplete, and that new discoveries will one day reveal an entirely new class of astrophysical objects that operate on principles we have yet to understand. What makes zombie stars even more compelling is that they challenge our fundamental assumptions about the nature of the universe itself. If stars can die and come back to life, what does that say about the larger cosmic forces at play? Could there be other objects, perhaps entire galaxies or even black holes, that experience similar cycles of destruction and rebirth? Could the universe itself be part of a larger cycle of death and regeneration that we have yet to perceive? These questions remind us that the cosmos is far more complex and mysterious than we often assume. While we have made incredible progress in understanding the mechanics of stars, galaxies, and black holes, there is still so much we do not know. Zombie stars stand as cosmic anomalies, strange, unexplainable beacons that hint at hidden forces shaping the universe in ways we do not yet comprehend. The search for answers continues. Scientists are now using some of the most advanced telescopes in the world, including the James Webb Space Telescope and next-generation observatories, to hunt for more zombie stars and analyze their properties in greater detail. By studying their light spectra, tracking their energy output, and searching for patterns in their behavior, astronomers hope to unlock the secrets of these undead stars and uncover the true nature of their impossible survival. Perhaps in the coming decades, we will find definitive explanations for these mysterious objects. Or perhaps they will remain one of the great unanswered questions of the universe, forever challenging our understanding of physics and the nature of existence. Either way, zombie stars have already earned their place among the most enigmatic and thought-provoking mysteries of the cosmos, serving as a reminder that the universe is still full of surprises, waiting to be uncovered. The study of zombie stars is not just about understanding a few rare, bizarre objects. It's about uncovering new laws of physics that could fundamentally change our perception of the universe. These stars challenge everything we thought we knew about stellar evolution, energy generation, and the limits of astrophysical phenomena. If a star can explode and then somehow reignite, it forces us to reconsider the fundamental principles that govern matter, gravity, and time itself. One of the most compelling aspects of zombie stars is that they blur the line between life and death on a cosmic scale. In most cases, when a star reaches the end of its life, the process is irreversible. A white dwarf will cool and fade, a neutron star will continue spinning but remain essentially dead in terms of new energy generation, and a black hole will trap anything that comes near it. But zombie stars break these rules. They refuse to remain dead. They somehow generate new bursts of energy after their apparent demise. This phenomenon raises deeper questions about the nature of stellar energy itself. Traditionally, a star shines because of nuclear fusion, where lighter elements fuse into heavier ones, releasing vast amounts of energy. However, in zombie stars, the source of energy is far less clear. Are they reigniting fusion through some unknown mechanism? Are they tapping into previously undetected sources of cosmic energy? Or are they revealing an entirely new state of matter that exists in extreme astrophysical conditions? Another intriguing possibility is that some zombie stars might be evidence of exotic stellar remnants that have not yet been classified. For example, scientists have theorized the existence of quark stars, hypothetical objects denser than neutron stars but not quite black holes. These objects could harbor strange forms of matter that behave in unpredictable ways, possibly allowing for intermittent bursts of energy long after a supernova. If zombie stars are actually quark stars or some other unknown stellar remnant, they could be the first direct evidence of physics that exists beyond the standard models of astrophysics. Additionally, the persistence of some zombie stars suggests that they might be interacting with forces that extend beyond the visible universe. Some theories propose that these stars might be linked to higher dimensional physics, where energy can be exchanged between different layers of reality. While this idea sounds like science fiction, it aligns with certain interpretations of string theory and brane cosmology, where the universe is not just a three-dimensional space but a complex, multidimensional structure where energy can leak from one domain into another. Even more puzzling is the fact that zombie stars do not seem to follow any predictable pattern. Some reignite within years, while others appear to reactivate centuries after their initial explosion. This randomness suggests that whatever process is causing them to return to life is either highly variable or is influenced by hidden factors we have yet to discover. Could the conditions of space itself, such as magnetic fields, dark matter interactions, or even cosmic radiation, be playing a role in their resurrection? There is also the possibility that zombie stars are not truly stars at all but rather some unknown form of cosmic entity that mimics stellar behavior. Some astrophysicists have speculated that highly magnetized neutron stars, known as Magnetars, could be mistaken for zombie stars when they undergo sudden outbursts of energy. Magnetars are known to release powerful bursts of X-rays and gamma rays, sometimes appearing to turn back on after long periods of dormancy. However, magnetars alone cannot explain all zombie stars, especially those that show repeated supernova-like explosions. One of the greatest challenges in studying zombie stars is their sheer unpredictability. Unlike other celestial objects, which follow well-understood cycles of formation, evolution, and decay, zombie stars do not fit into any established model. Their appearances and behaviors seem almost random, making it difficult for astronomers to study them systematically. But what if zombie stars are not just isolated anomalies but instead represent an entire class of astrophysical objects that have simply gone undetected until now? If we were to discover more of them, it might suggest that stellar death is not always a final event but rather part of a much longer, more complex process that can extend across millennia. This would mean that the life cycles of stars are far more intricate than we ever imagined, possibly involving multiple phases of destruction and rebirth rather than a single, linear progression from birth to death. The implications of this discovery would be profound. It would mean that the universe is not just a vast graveyard of dying stars but a dynamic, ever-changing system where even the most extreme cosmic events are not necessarily the end of the story. If stars can die and then be reborn, it raises the possibility that entire galaxies or even the universe itself might undergo similar cycles of death and renewal. Some cosmologists have even suggested that the concept of a zombie universe might not be far-fetched. Just as individual stars can seemingly return to life, what if the entire cosmos operates on a similar principle? What if the universe itself undergoes cycles of expansion, collapse, and re-expansion, effectively resurrecting itself over and over again? This idea aligns with certain models of cyclic cosmology, where the Big Bang was not the beginning of everything but simply the latest phase in an eternal sequence of cosmic rebirths. Ultimately, the mystery of zombie stars reminds us that the universe is far from being fully understood. Every time we think we have the cosmos figured out, new discoveries emerge that challenge our assumptions and force us to rethink the fundamental laws of physics. The existence of stars that refuse to die is one of the most compelling pieces of evidence that our understanding of reality is still incomplete. In the coming years, as telescopes become more powerful and new observational techniques are developed, we may finally uncover the true nature of these enigmatic stars. Perhaps we will find that they are remnants of an unknown type of stellar object, or maybe they will lead us to entirely new branches of physics. Whatever the case, zombie stars serve as a cosmic riddle, one that continues to defy explanation and push the boundaries of human knowledge. And so, the search for answers continues. Scientists will keep scanning the skies, looking for more signs of stars that refuse to die, hoping to unlock the secrets of these celestial anomalies. But for now, Zombie stars remain one of the universe's most tantalizing mysteries, a phenomenon that challenges everything we thought we knew about the life and death of stars, and perhaps even the nature of existence itself. The enigma of zombie stars extends far beyond their immediate scientific implications. It touches on the very nature of reality itself. If these objects exist, refusing to conform to our models of stellar death, it raises profound questions about the laws of physics, the structure of the cosmos, and even our understanding of time. Could these stars be hinting at a deeper, hidden mechanism of the universe, something we have yet to grasp? Or are we simply witnessing rare, extreme events that push the boundaries of what we thought was possible? One of the most startling aspects of zombie stars is how they appear to defy entropy. According to the second law of thermodynamics, systems tend toward disorder, and energy disperses over time. Stars, once they exhaust their fuel, should not be able to spontaneously reignite. Yet zombie stars seem to break this fundamental rule, experiencing repeated surges of energy long after they should have burned out. This suggests that some unknown process, one beyond our current understanding of astrophysics, is at work. One possible explanation lies in the realm of quantum mechanics. In classical physics, a supernova marks the end of a star's life, a one-way transformation from order to chaos. But at the quantum level, things are far less predictable. Quantum fluctuations allow for temporary reversals of entropy, where particles and energy can spontaneously appear and disappear. Could zombie stars be exploiting some unknown quantum effect, allowing them to tap into hidden energy reserves or even draw power from the vacuum of space itself? Another possibility is that zombie stars interact with dark matter in a way we have not yet discovered. Dark matter, which makes up most of the universe's mass but remains invisible to our instruments, could play a role in reviving stars after their deaths. Some theorists propose that if dark matter can interact with regular matter under specific conditions, it might provide a fresh energy source that reignites dying stars. If this hypothesis proves correct, zombie stars could be a crucial key to unlocking the secrets of dark matter, one of the greatest unsolved mysteries of modern physics. But what if the answer lies not in the star itself but in its surrounding environment? The space around a supernova remnant is filled with turbulent forces, powerful magnetic fields, intense gravitational distortions, and swirling clouds of plasma. In some cases, these extreme conditions might trigger bizarre astrophysical effects that temporarily reactivate stellar cores. For example, it's possible that zombie stars are actually pulsars, rapidly spinning neutron stars whose magnetic fields accelerate particles to near light speed. If a pulsar's rotation slows down and then suddenly speeds up again due to an external influence, it might give the appearance of a star coming back to life. Alternatively, these stars may be tapping into exotic physics that only occur under extreme conditions. Some theories propose the existence of axions, hypothetical particles that could influence the behavior of dying stars. If axions exist, they might convert into photons under intense magnetic fields, injecting new energy into a dead star and making it appear to reignite. This idea is purely theoretical, but if proven true, it could open an entirely new field of physics, with implications far beyond astrophysics. Zombie stars could also be a natural consequence of stellar cannibalism. In binary star systems, where two stars orbit each other, a dead star can sometimes siphon material from its companion, effectively stealing its fuel. If enough material accumulates, the dead star might briefly reignite, causing it to emit bursts of radiation and even mimic a small supernova. This process, known as accretion-induced collapse, has been observed in some white dwarfs, which suddenly brighten before collapsing into neutron stars. However, this explanation does not account for zombie stars that reignite long after their supposed deaths, nor does it explain cases where no companion star is present. Another puzzling aspect of zombie stars is their unpredictability. Unlike regular supernovae, which follow a clear life cycle, these objects seem to reactivate at random intervals. Some appear to reignite only once, while others flare up multiple times over centuries. This erratic behavior suggests that we are dealing with a phenomenon that does not fit into any known astrophysical model. One theory suggests that zombie stars might be remnants of a failed hypernova, an extremely powerful supernova that does not completely destroy the star. In some cases, the explosion may only partially disrupt the star, leaving behind a smoldering core that reignites under the right conditions. This could explain why some zombie stars experience multiple explosive events. They are undergoing a slow, drawn-out death rather than a single catastrophic event. But perhaps the strangest possibility is that zombie stars are evidence of new physics beyond the standard model. Some speculative theories suggest that extreme astrophysical objects might serve as gateways to higher dimensions or exotic forms of matter. If this is the case, then zombie stars might be more than just resurrected stars. They could be manifestations of physical laws that operate differently in certain regions of the cosmos. For example, some versions of string theory propose that extra dimensions could allow energy to leak into our universe from a parallel realm. If true, then zombie stars might be tapping into a hidden energy reservoir that exists beyond our normal three-dimensional space. This would explain why they appear to defy conventional physics, as they might be operating under rules that do not apply to regular stars. There is also the possibility that zombie stars are related to black holes in a way we do not yet understand. While black holes are known for consuming everything that falls into them, some theories suggest that they might also be capable of ejecting energy under specific conditions. If a dying star were near a black hole, it could be affected by strange gravitational interactions that momentarily reignite its core. This could create the illusion of a star coming back to life when, in reality, it is simply being influenced by a much larger cosmic force. Regardless of the explanation, zombie stars challenge our understanding of the universe in ways that few other discoveries have. They remind us that the cosmos is still full of mysteries and that even the most fundamental laws of physics may not be as absolute as we once thought. As astronomers continue to study these enigmatic objects, they may uncover insights that not only explain zombie stars but also reshape our understanding of stellar evolution, dark matter, quantum mechanics, and the very nature of reality itself. Perhaps one day, we will look back at these strange, undead stars as the first clues in a much larger puzzle, one that ultimately leads us to a deeper, more complete understanding of the cosmos. But until that day comes, zombie stars remain one of the most baffling and fascinating phenomena in the universe, a cosmic mystery that refuses to die, just like the stars themselves. The mystery of zombie stars is not just a question of astrophysics. It is a fundamental challenge to how we understand the very fabric of the universe. If stars can reignite after death, does that mean the finality of stellar collapse is not as absolute as we once thought? Could this phenomenon suggest an entirely new category of stellar life cycles, ones that we have yet to comprehend? The implications of these questions stretch far beyond astronomy and into the realm of physics, cosmology, and even philosophy. One of the most perplexing aspects of zombie stars is their apparent violation of known energy conservation laws. In standard astrophysical models, a star dies when it exhausts its nuclear fuel, leading to either a white dwarf, neutron star, or black hole. The sudden reignition of a supposedly dead star suggests that either an unknown energy source is at play or that the energy dynamics within a star's core are more complex than we currently believe. One possible explanation involves an exotic state of matter known as quark matter. In the extreme conditions of a neutron star's core, where densities are unimaginably high, quarks, the fundamental building blocks of protons and neutrons, might exist freely instead of being confined inside atomic nuclei. If certain conditions trigger a phase transition in this quark matter, it could release energy in a way that temporarily reactivates the dead star. This would not be a true resurrection in the classical sense, but rather a delayed burst of energy caused by the exotic physics occurring deep within the remnant. Another theory suggests that zombie stars may be a form of a failed black hole. Normally, when a massive star collapses under its own gravity, it either becomes a neutron star or a black hole, depending on its mass. However, in certain rare conditions, a star might hover on the edge of becoming a black hole but not quite cross the threshold. If some external factor, such as a sudden influx of matter or a powerful magnetic interaction, prevents full collapse, the star might experience temporary rebirths as it oscillates between states. This could explain why some zombie stars appear to erupt multiple times, as they exist in a delicate balance between life and death. There is also the possibility that zombie stars are a byproduct of interactions with exotic cosmic phenomena like cosmic strings or wormholes. Cosmic strings are hypothetical one-dimensional defects in spacetime that formed in the early universe, potentially acting as conduits for massive amounts of energy. If a zombie star were somehow linked to a cosmic string, it might intermittently draw energy from this structure, reigniting its core in unpredictable bursts. Similarly, if wormholes exist, they could provide a hidden energy reservoir that periodically rejuvenates a dying star. The more we study these stellar anomalies, the more they seem to hint at the existence of unknown forces operating in the universe. Could it be that zombie stars are the result of physics beyond the standard model? Some physicists speculate that these objects might interact with hypothetical particles that exist outside of known physics, such as sterile neutrinos or hidden sector particles. If zombie stars are influenced by these unknown forces, they could provide one of the first observable clues to a larger cosmic structure we have yet to understand. There is also a deeper, more unsettling question: are zombie stars a unique phenomenon, or are they simply an extreme example of a more widespread process? If stars can reignite after death, could other celestial objects exhibit similar properties? What if planets, galaxies, or even entire sections of the universe experience periodic rebirths, governed by forces we do not yet comprehend? The study of zombie stars might ultimately lead us to a more fundamental truth about the universe itself. Perhaps these stars are the first evidence that the universe does not operate in a linear fashion but rather in cycles of creation, destruction, and rebirth. If so, our understanding of cosmic evolution would need to be rewritten entirely. Regardless of the answer, one thing is certain: zombie stars remain one of the most baffling, awe-inspiring mysteries in astrophysics. They defy our expectations, challenge our models, and force us to reconsider what we thought we knew about the life and death of stars. As technology advances and telescopes become more powerful, we may one day unlock the secrets of these stellar revenants. Until then, they will continue to haunt the cosmos, flickering back to life when all logic says they should be gone forever. The existence of zombie stars suggests that the universe is far stranger than we ever imagined. These celestial anomalies challenge the very foundation of astrophysics, hinting at forces and mechanisms we have yet to uncover. If stars can defy death and reignite, then the universe may hold other secrets that rewrite our understanding of cosmic evolution. Could zombie stars be the first observable evidence of an underlying cosmic process that applies not just to stars but to entire galaxies, or even the fabric of reality itself? One possibility that has intrigued physicists is the idea that these stars are remnants of a multiverse interaction. Some theories suggest that our universe is not the only one, but rather part of a vast multiverse, with different regions of reality interacting in ways we cannot yet perceive. If zombie stars are tapping into energy from an alternate dimension, they could be the first tangible evidence of a connection between universes. This would mean that stellar death is not always a final event but instead a gateway to unknown realms of physics. Another speculative idea is that zombie stars are demonstrating a form of cosmic recycling, where the universe itself has built-in mechanisms for reusing matter and energy in ways we do not yet understand. While black holes have long been thought to serve as the ultimate endpoints of stellar collapse, what if some stars experience a different fate? Instead of collapsing into oblivion, they might undergo a series of rebirths, suggesting that the universe is designed to sustain energy and structure far longer than we once believed. The behavior of zombie stars also raises questions about the true nature of entropy. In classical thermodynamics, entropy dictates that systems move toward disorder, and stellar death should be a one-way process. But if some stars can defy this rule and reignite, it might mean that entropy is more complex than we realize, perhaps even reversible under certain conditions. If true, this would have profound implications not only for astrophysics but also for fields like quantum mechanics and cosmology. Could it be that the universe has hidden mechanisms that allow for localized reversals of entropy, bringing dead stars back to life? Another hypothesis is that zombie stars are deeply connected to dark energy, the mysterious force driving the accelerated expansion of the universe. If dark energy interacts with stellar remnants in ways we do not yet understand, it might provide bursts of energy that temporarily reignite dead stars. This would mean that zombie stars are not just rare astrophysical phenomena but key indicators of how dark energy operates on a local scale. If we can decipher the physics behind these resurrections, we might gain crucial insights into the fundamental forces shaping the cosmos. Yet, for all the potential explanations, one thing remains clear: zombie stars are not behaving in a way that fits within our current models of stellar life cycles. Whether they are being reignited by unknown quantum effects, interacting with exotic particles, or even tapping into energy from alternate dimensions, they demand a complete rethinking of what we know about stars and their fate. The study of zombie stars is still in its infancy, but as technology advances, we may one day uncover their true nature. Perhaps in the coming decades, new telescopes and space observatories will detect more of these bizarre objects, allowing astronomers to piece together the puzzle. Until then, zombie stars remain one of the greatest mysteries of the cosmos, a testament to the fact that the universe still holds secrets beyond our wildest imagination. Zombie stars defy our understanding of life, death, and rebirth in the cosmos, and their very existence forces us to reconsider some of the most fundamental laws of physics. How can a star, once exploded and reduced to what should be an inert core, suddenly reignite with newfound energy? Where does this energy come from? Is it a quirk of extreme astrophysics, an effect of exotic matter, or even a sign of forces we have yet to discover? These questions push the boundaries of modern astronomy, and the deeper we look into the phenomenon of zombie stars, the more perplexing and profound the mystery becomes. At its core, the paradox of zombie stars revolves around the apparent contradiction of energy conservation. When a star explodes in a supernova, the remaining core is expected to cool down over time, transitioning into a white dwarf, neutron star, or black hole. These are the traditional endpoints of stellar evolution, where fusion ceases, and only residual heat slowly radiates away. Yet zombie stars appear to undergo a different fate. They flare up again, sometimes multiple times, defying all predictions. One possible explanation involves the presence of an unstable nuclear reaction within the remnants of the star. Some researchers speculate that certain elements left behind after a supernova, such as nickel-56 or other radioactive isotopes, could experience delayed decay processes that release energy in unpredictable ways. However, this theory does not fully explain cases where the star appears to reignite long after the expected decay period. If it were merely a matter of radioactive decay, the energy output would gradually decline, not suddenly surge back to supernova levels. Another possibility is that these zombie stars are not reigniting from within, but rather being externally triggered by matter falling back onto them. In many supernova events, a significant amount of the original star's mass is ejected outward, but some of this material might eventually be pulled back by gravity. If enough of this material falls onto the remnant core at just the right moment, it could create a new burst of nuclear fusion, briefly reviving the star. However, this explanation still has difficulties, such as explaining why some zombie stars appear to experience multiple bursts of activity over long periods of time. There is also the possibility that zombie stars are linked to the presence of exotic matter, such as quark matter or strange matter. Quark matter is a theorized form of ultra-dense matter that might exist inside neutron stars, composed of free quarks rather than protons and neutrons. If certain conditions cause a phase transition within this matter, it could lead to sudden energy releases, essentially causing the dead star to temporarily reignite. Even more speculative is the idea of strange matter, a hypothetical form of matter so stable that it could spread like a virus, converting ordinary matter into its own exotic state. If a zombie star contains pockets of strange matter, it could trigger periodic outbursts as it interacts with normal matter in unpredictable ways. Another fascinating possibility involves dark matter interactions. Dark matter is thought to make up most of the mass in the universe, yet it barely interacts with normal matter except through gravity. Some astrophysicists have proposed that in certain extreme environments, dark matter might occasionally interact with ordinary matter in ways we do not yet understand. If a zombie star were to accumulate a dense cloud of dark matter, there might be rare interactions that cause localized bursts of energy, explaining the seemingly random reignition events. Even more extreme theories suggest that zombie stars could be influenced by phenomena outside our conventional understanding of physics, such as wormholes or cosmic strings. Wormholes are hypothetical bridges in spacetime that could connect different regions of the universe, or even different universes. If a dying star were somehow linked to a wormhole, it could periodically draw in energy from another part of spacetime, temporarily bringing it back to life. Similarly, cosmic strings, ultra-thin defects in spacetime left over from the early universe, could interact with stellar remnants in ways that release bursts of energy. While these ideas are highly speculative, they highlight just how bizarre and unexpected the universe can be. The implications of zombie stars go beyond just stellar physics. If these stars are experiencing repeated cycles of death and rebirth, it raises fundamental questions about the nature of cosmic evolution itself. Are these stars unique anomalies, or are they part of a larger, yet undiscovered process governing the life cycle of celestial objects? Could galaxies, or even entire regions of the cosmos, experience similar cycles of destruction and rebirth on a much grander scale? Moreover, the existence of zombie stars might suggest that energy in the universe is not as easily lost as we once thought. If these stars can somehow reignite after death, it could mean that the universe has built-in mechanisms for recycling energy and matter in ways that go beyond our current models of entropy. This would have profound implications not only for astrophysics, but also for the study of cosmology and the ultimate fate of the universe. One of the most intriguing possibilities is that the study of zombie stars might lead to breakthroughs in our understanding of dark energy, the mysterious force driving the expansion of the universe. If dark energy interacts with dying stars in ways that allow them to temporarily reignite, it could provide a crucial clue about its nature. Some theories suggest that dark energy might not be a uniform force but rather something that interacts with matter under specific conditions. If zombie stars are somehow tapping into this force, they could be providing us with a natural laboratory for studying one of the greatest unsolved mysteries in modern physics. As telescopes become more powerful, and as new observational techniques are developed, astronomers are likely to uncover more zombie stars lurking in the cosmos. Each new discovery adds another piece to the puzzle, helping us refine our theories and rule out certain possibilities. But for now, these strange, undead stars remain one of the most baffling and awe-inspiring phenomena in the universe. They challenge our assumptions, defy our expectations, and remind us that the cosmos is still filled with secrets waiting to be uncovered. Zombie stars are not just a curiosity, they are a window into the unknown, a glimpse at the deeper mysteries of existence that science has yet to unravel. Whether they are fueled by exotic matter, dark energy interactions, or processes we have not yet imagined, they stand as a testament to the sheer complexity and wonder of the universe. With each new observation, we move one step closer to understanding their true nature, but until then, they remain an enigma, silent, flickering beacons of a universe far stranger than we ever dared to dream. If zombie stars can reignite after death, it forces us to reconsider everything we thought we knew about the life cycle of stars. Traditionally, astrophysics has taught us that stars are born, live by fusing hydrogen into heavier elements, and die either in a spectacular supernova or by gradually cooling into white dwarfs. This process is supposed to be a one-way street, governed by the irreversible laws of thermodynamics. But zombie stars challenge that assumption. They do not simply die and fade away, they come back, sometimes multiple times, defying our expectations. The fact that some stars refuse to stay dead suggests that the universe has hidden processes at work, operating outside our current understanding of stellar evolution. To truly grasp the significance of zombie stars, we must take a step back and examine the fundamental forces that govern the cosmos. At the heart of every star is a balance between two opposing forces, gravity and radiation pressure. Gravity pulls inward, trying to collapse the star under its immense weight, while radiation pressure, generated by nuclear fusion, pushes outward, preventing collapse. This delicate equilibrium determines a star's entire life cycle. But when a star exhausts its nuclear fuel, radiation pressure weakens, and gravity wins, causing the star to collapse. The specific outcome, whether it becomes a white dwarf, neutron star, or black hole, depends on its mass. Zombie stars, however, disrupt this narrative. They suggest that under certain conditions, a star's core can reignite even after it has supposedly died. But where does this extra energy come from? One possibility is that some stars have hidden reserves of nuclear fuel that only become accessible under extreme conditions. In most stars, fusion occurs in the core, where temperatures and pressures are highest. However, in some cases, fusion might be reignited in the outer layers of the remnant star, producing bursts of energy that momentarily bring the star back to life. Another possibility is that some supernovae do not completely destroy their progenitor stars. Instead of being obliterated, the core might survive, buried under layers of ejected material. If this remnant core remains hot enough, it could pull back some of the surrounding matter and reignite nuclear fusion, leading to the bizarre flickering behavior observed in some zombie stars. This would mean that some stars only, partially, die, existing in a liminal state between death and rebirth. Some researchers have proposed that zombie stars could be linked to highly magnetized neutron stars, known as magnetars. Magnetars are a rare type of neutron star with magnetic fields trillions of times stronger than Earth's. These fields can twist and snap, releasing enormous amounts of energy in the form of gamma-ray bursts. If a dead star somehow interacts with a nearby magnetar, it could trigger sudden bursts of energy that mimic the appearance of a star reigniting. This would mean that zombie stars are not self-contained phenomena but are instead part of a larger cosmic network, influenced by their environment in ways we do not yet fully understand. Another compelling theory involves the role of accretion. In binary star systems, a dead star might siphon material from its companion, gradually accumulating enough mass to reignite fusion. This process, known as accretion-induced collapse, has been observed in some white dwarfs, which explode as type Ia supernovae when they reach a critical mass. However, in the case of zombie stars, this process appears to be more erratic and unpredictable, with the star experiencing multiple bursts of activity rather than a single catastrophic explosion. Could zombie stars be the missing link in our understanding of stellar recycling? If these stars are capable of reigniting after death, it suggests that stellar remnants might not be as inert as we once believed. Instead of being cosmic corpses, they might play an active role in redistributing energy and matter throughout the universe. This idea ties into the broader concept of cosmic renewal, where destruction and creation are not separate processes but part of a continuous cycle. If zombie stars are capable of defying death, then what other celestial objects might have hidden layers of complexity? Could entire galaxies, or even the universe itself, undergo cycles of death and rebirth on a grander scale? The concept of zombie stars also forces us to reconsider the role of entropy in the universe. In classical thermodynamics, entropy dictates that systems move toward increasing disorder. A star's death should be the ultimate expression of entropy, as its structured nuclear processes come to an end. Yet zombie stars suggest that under certain conditions, entropy might be locally reversible. If true, this could have profound implications for our understanding of the arrow of time and the fundamental nature of reality itself. One of the strangest possibilities is that zombie stars are interacting with unknown particles or forces that we have not yet discovered. Some physicists have speculated that they might be tapping into reservoirs of exotic energy, perhaps even linking to dark energy or dark matter in unexpected ways. If dark energy is responsible for the accelerated expansion of the universe, could it also influence dying stars, providing the extra push needed to reignite them? This would mean that zombie stars are not just astrophysical oddities but key pieces of evidence in solving one of the greatest mysteries in cosmology. Even more radical is the idea that zombie stars could be evidence of quantum effects on a macroscopic scale. Quantum mechanics allows for particles to temporarily borrow energy from the vacuum of space, a process known as quantum fluctuation. If a similar mechanism operates on a larger scale, it could explain how zombie stars intermittently gain bursts of energy seemingly out of nowhere. This would be groundbreaking because it would suggest that quantum mechanics and astrophysics are more deeply interconnected than we ever imagined. Ultimately, zombie stars challenge our assumptions about how the universe works. Their existence suggests that the cosmic order is not as rigid as we once believed, that even in death, stars can find a way to persist, to defy the laws that should govern them. Whether they are fueled by hidden nuclear reactions, dark matter interactions, or even exotic quantum effects, they stand as a testament to the fact that the universe is still full of surprises. As we continue to study these enigmatic objects, we may uncover deeper truths about the nature of stellar evolution, energy conservation, and even the fundamental laws of physics. Each new discovery brings us closer to understanding the forces at play, but for now, zombie stars remain an enigma, an unresolved mystery that beckons us to look deeper into the cosmos and question everything we thought we knew. The more we learn about the universe, the more it seems to resist easy explanations. And perhaps that is the greatest mystery of all, that in a cosmos filled with patterns, laws, and predictable cycles, there are still things that refuse to conform, that defy expectations and force us to reconsider the very fabric of reality itself. Zombie stars are not just dying stars, they are cosmic paradoxes, flickering testaments to the boundless complexity of the universe, and reminders that the cosmos is far from fully understood. If zombie stars truly exist as cosmic anomalies, they could serve as a window into the deeper mechanics of the universe, ones we have yet to fully grasp. Their ability to reignite after apparent death raises fundamental questions about the nature of stellar remnants, energy transfer, and the very fate of celestial bodies. Could this phenomenon be more widespread than we realize? Could there be entire galaxies where stars refuse to die completely, cycling through life and death in ways that contradict our standard models? One of the key areas where zombie stars challenge our understanding is the role of extreme conditions in stellar evolution. Traditional models assume that when a star explodes as a supernova, it either collapses into a black hole, a neutron star, or disperses completely, leaving behind only remnants of gas and dust. But zombie stars suggest that some stellar remnants retain enough energy or external influence to sustain periodic bursts of activity. This means that the death of a star is not always final. It can be drawn out over time, manifesting as sudden flashes of energy, or even temporary resurgences of brightness. This unpredictability complicates our ability to classify and predict the behavior of supernovae. Normally, Type I supernovae, explosions of white dwarfs, are considered standard candles in astronomy, meaning they have a predictable brightness used to measure cosmic distances. But if some stars can reignite unexpectedly, it raises doubts about how reliable these standard candles truly are. Could there be undiscovered variations of supernovae that behave in ways we have not accounted for? Could zombie stars be distorting our understanding of the universe's expansion? If even a small percentage of white dwarfs have the potential to reignite under unknown conditions, it could introduce significant uncertainties into cosmological calculations. One potential clue lies in pulsations observed in certain white dwarfs and neutron stars. Some stars exhibit periodic changes in brightness, suggesting that their interiors undergo complex and unpredictable processes. One hypothesis is that material from previous explosions remains trapped in a delicate balance, oscillating between dormancy and ignition. This could be due to instabilities in nuclear fusion, magnetic field interactions, or even gravitational effects from nearby objects. Magnetic fields play a particularly intriguing role in this mystery. The presence of ultra-strong magnetic fields in some zombie stars could explain their ability to flare up unexpectedly. In a magnetar, a type of neutron star with a magnetic field trillions of times stronger than Earth's, energy is stored in twisted magnetic lines. When these lines snap and reconnect, they release bursts of radiation, sometimes so powerful they can be detected from other galaxies. Could zombie stars be experiencing a similar process, with buried magnetic fields occasionally unleashing trapped energy? If so, this would mean that some stars die with residual magnetic energy capable of reigniting fusion-like processes in short bursts. Accretion, the process of gathering material from a nearby object, also offers a possible explanation. If a white dwarf or neutron star orbits another star in a binary system, it can steal material from its companion. As this material piles up, it can occasionally trigger nuclear reactions on the surface of the dead star, causing brief, supernova-like eruptions. This is similar to classical novae, where white dwarfs temporarily brighten due to runaway fusion on their surfaces. However, in the case of zombie stars, the process appears to be less predictable, with energy releases occurring at irregular intervals. Another strange possibility is that zombie stars are interacting with exotic matter, perhaps even dark matter. Dark matter makes up most of the mass in the universe, yet we still do not know what it is. Some theories suggest that if dark matter interacts weakly with normal matter, it could accumulate in stellar remnants, subtly affecting their behavior. If dark matter can be captured in the core of a dying star, it could potentially provide a new energy source, leading to unexpected bursts of activity long after the star should have gone dark. Even more radical ideas propose that zombie stars could be interacting with hypothetical objects such as primordial black holes, tiny black holes that might have formed in the early universe. If such objects exist, they could occasionally pass through or become trapped inside stellar remnants, disrupting their equilibrium and causing periodic flares of energy. This could mean that zombie stars are not only astrophysical oddities but also indirect evidence of phenomena we have yet to observe directly. Some scientists speculate that zombie stars could also be connected to failed supernovae, events where a star appears to collapse into a black hole but instead lingers in a strange, intermediate state. Normally, when a massive star runs out of fuel, it either explodes as a supernova or collapses entirely into a black hole. However, recent observations suggest that some stars vanish without a traditional explosion, leading to speculation that they might undergo a different, less understood form of stellar death. If these failed supernovae occasionally reignite due to unknown processes, they could explain the intermittent behavior observed in some zombie stars. What if zombie stars are not just isolated phenomena but part of a broader, cosmic cycle that we have yet to recognize? If stars can flicker between states of death and rebirth, could this imply a deeper principle governing the universe? Some physicists have suggested that the cosmos itself might operate on a principle of cyclical renewal, where even seemingly dead objects retain the potential for rebirth under the right conditions. In this sense, zombie stars might serve as an analogy for the universe itself. Just as these stars refuse to die completely, could the universe undergo cycles of expansion, collapse, and rebirth? The idea of a cyclic universe, where the cosmos continually regenerates itself, has been proposed in various forms, from the ancient concept of the eternal return to modern theories of the Big Bounce, where each cosmic era follows the death of a previous one. Could zombie stars be microcosmic examples of this grand cosmic cycle, hinting that death in the universe is never absolute but merely a transition into another state? If so, then the existence of zombie stars could be more than an astronomical curiosity. It could be a clue that nature, at every scale, finds ways to resist finality. This perspective challenges one of the most fundamental assumptions in physics, entropy. The second law of thermodynamics states that in a closed system, entropy always increases, meaning that systems naturally tend toward disorder and decay. A dying star should be the ultimate example of this. Having exhausted its nuclear fuel, it should collapse into a final state from which it cannot return. And yet, zombie stars seem to find ways to defy this principle, briefly reversing their decay and reigniting in spectacular bursts of energy. If this defiance is not just a one-off anomaly but a pattern found in multiple locations across the cosmos, it suggests that the laws governing stellar life cycles are incomplete. What if, under certain extreme conditions, energy can be temporarily reorganized in ways that defy entropy's usual march toward disorder? Could there be feedback mechanisms in stellar remnants that periodically reset energy distributions, allowing short-lived flashes of renewed activity? If so, this could hint at deeper, hidden structures in physics, ones that only reveal themselves in the most extreme environments. Even more mind-bending is the idea that some zombie stars might never truly die at all. Certain theoretical models propose that instead of fully collapsing into neutron stars or black holes, some stars might enter an exotic, ultra-dense state where they hover in a limbo between existence and destruction. These objects, sometimes called quark stars or even strange stars, are thought to be composed of ultra-compressed matter beyond the neutron level, possibly even forming exotic phases of quark gluon plasma. If some zombie stars are actually failed black holes, where collapse was halted by an unknown process, then they could behave unpredictably, occasionally releasing energy as their internal structure shifts. This would mean that the objects we see flaring up again and again could be neither dead stars nor fully functioning stars, but something in between, a new category of celestial body that challenges our very definitions of what stars are. Another possibility lies in the behavior of white dwarfs under extreme conditions. Most white dwarfs slowly cool over time, fading into inert black dwarfs. However, under certain circumstances, white dwarfs could experience delayed thermonuclear events, where unstable fusion reignites for short periods. If small amounts of helium or hydrogen remain trapped within a white dwarf's outer layers, they could periodically undergo fusion bursts, leading to temporary increases in brightness that mimic a star returning to life. This could mean that many more zombie stars exist than we currently realize, but we simply lack the observational timeframes to detect them. Since these resurgences could occur on timescales of centuries or millennia, we might only be catching glimpses of this phenomenon. If we had the ability to observe a single stellar remnant over millions of years, we might find that what we assumed were dead stars are actually cycling through long, drawn-out periods of activity and dormancy. Beyond the scientific implications, zombie stars hold a kind of poetic significance. They embody the idea that even in the depths of destruction, there can be new bursts of creation. The cosmos is often thought of as a place of vast, cold finality, where stars burn out and galaxies drift into darkness. But if zombie stars are real, they suggest that the universe has ways of resurrecting its own structures, finding moments of light even where none should exist. If we look at this idea from a cosmic scale, it forces us to rethink not just how stars behave but how the entire universe functions. Could the universe itself be structured in such a way that energy is never truly lost, only repurposed in unpredictable ways? Could the very fabric of spacetime allow for temporary reversals of stellar death, hinting at deeper layers of physics that we have yet to comprehend? This leads to one of the most profound questions of all. If stars can defy death, what does that say about the nature of reality itself? Could there be unknown principles at play that allow energy and matter to persist in ways we have not yet imagined? And if so, what else in the cosmos might be capable of similar resurrections? Zombie stars are more than just strange anomalies. They are windows into the unknown. They remind us that the universe is not as predictable as we once thought, that even the most well-established rules of physics may have exceptions. They challenge us to rethink what we consider possible, pushing the boundaries of science into realms of speculation, mystery, and wonder. And if we keep searching, if we continue to push the limits of our understanding, who knows what other cosmic resurrections we might one day uncover? Perhaps zombie stars are just the beginning, a sign that the universe still holds secrets waiting to be unraveled, mysteries that, like these stars, refuse to fade into the void. If zombie stars represent a larger cosmic pattern, then their existence could hint at principles of energy recycling that extend far beyond individual stellar remnants. This idea forces us to reconsider how the universe maintains equilibrium over time. Are these stars evidence that some form of cosmic balance exists, where energy is never truly lost but rather redistributed in unexpected ways? Could there be processes we have yet to discover that regulate the life and death cycles of celestial objects? One of the most intriguing possibilities is that zombie stars could be the key to understanding the ultimate fate of the universe itself. Current cosmological theories suggest that the universe is expanding at an accelerating rate, driven by the mysterious force known as dark energy. If expansion continues unchecked, the cosmos may eventually experience heat death, a state where all energy is evenly spread out, and no further work can be done. But what if zombie stars are evidence that, on some level, energy can spontaneously reorganize itself, even in seemingly final states? If stars can reignite after their supposed deaths, could entire galaxies or even the universe itself undergo similar rebirths? This notion ties into the idea of cosmic cycles, where the universe may not be heading toward a single, irreversible end but rather oscillating between phases of creation and destruction. Some cosmologists have proposed models where the universe undergoes repeated cycles of expansion and contraction, an idea known as the Big Bounce. If zombie stars can persist through explosions and reignite against all expectations, could they be microcosmic examples of this grander phenomenon? Another possibility is that zombie stars might be interacting with unknown physical forces that we have yet to understand. If dark energy and dark matter play a role in their resurrection, this could provide valuable clues about the nature of these elusive components of the universe. Dark matter, in particular, is one of the greatest mysteries in modern physics. It makes up the majority of mass in the cosmos, yet we cannot see or directly detect it. Could zombie stars be feeding off dark matter in some way, using it as an energy source to trigger their unexpected flares? Some theories suggest that if dark matter consists of exotic particles capable of interacting weakly with ordinary matter, then under extreme conditions, such as the intense gravitational fields of stellar remnants, it might become trapped and compressed. If enough dark matter accumulates within a dead star, it could potentially trigger reactions that release bursts of energy. This would mean that zombie stars are not merely stellar flukes but rather key indicators of new physics that extend beyond our current understanding. There is also the possibility that zombie stars are not unique to our own universe. If we consider the hypothesis of the multiverse, where countless parallel universes might exist, each with different physical laws, then it raises the question of whether these stars are evidence of cosmic overlap. Could zombie stars be interacting with remnants from other realities, experiencing brief periods of energy transfer from unknown dimensions? While this idea remains speculative, it aligns with some interpretations of quantum mechanics that suggest the universe is far more interconnected than we realize. On a more practical level, the study of zombie stars could have direct implications for our own survival as a species. If we can learn how some stars manage to reignite after death, we might uncover principles that could one day help humanity manipulate energy in entirely new ways. Could the processes sustaining these stars be harnessed to create long-lasting energy sources? Could understanding how they delay final collapse help us develop new technologies for sustaining artificial fusion reactions, perhaps even leading to breakthroughs in interstellar travel? These stars also challenge our notions of permanence and finality. Throughout history, humanity has looked to the stars as symbols of endurance, yet we have also accepted that they have lifespans dictated by immutable physical laws. The discovery that some stars can resist this fate, albeit temporarily, suggests that the cosmos is far more unpredictable than we assumed. This unpredictability reminds us that even the most well-established scientific principles may still hold surprises, that our understanding of the universe is still in its infancy, and that there are forces at play that we have yet to fully grasp. If zombie stars can exist, what other unknown stellar phenomena might be out there? Are there stars that can reignite not just once, but multiple times across eons, effectively making them immortal? Could there be other objects in the cosmos that defy destruction in even stranger ways? And if so, what does that say about the fundamental nature of matter, energy, and time itself? Perhaps the greatest lesson of zombie stars is that the universe is never as simple as we expect it to be. Every time we believe we have figured out the rules governing existence, the cosmos finds a way to surprise us. These stars are a testament to the endless complexity of reality, a reminder that even in the vast emptiness of space, the story is far from over. As we continue to study these anomalies, we may find that zombie stars are not just rare outliers, but hints of a much larger, deeper truth about the universe. They may be revealing secrets that have been hiding in plain sight, waiting for us to finally notice. And when we do, it may change everything we thought we knew about the cosmos. If zombie stars hint at a larger cosmic mystery, then their implications could stretch far beyond astrophysics, potentially reshaping our understanding of the fundamental forces governing reality itself. These celestial phenomena defy what we expect from stellar evolution, suggesting that energy and matter may not always behave according to the rules we have established. Instead of following a predictable pattern of birth, fusion, and death, some stars appear capable of rebirth, though only briefly, before plunging back into darkness. This paradox raises one of the most profound questions in physics. Is there truly an irreversible end to anything in the universe? At its core, This question challenges the nature of entropy, the principle that dictates that systems naturally move toward disorder over time. According to classical thermodynamics, once a star exhausts its nuclear fuel and collapses, there should be no coming back. Yet, zombie stars defy this notion by momentarily regaining brightness, as if some hidden mechanism allows them to reclaim energy from their surroundings. If this phenomenon is widespread, it suggests that our understanding of stellar death is incomplete, perhaps even incorrect in some key ways. One potential explanation could involve quantum effects on a cosmic scale. In quantum mechanics, particles can exist in superposition, where they hold multiple states at once until observed. Could it be possible that dead stars, under extreme gravitational conditions, briefly enter a quantum-like limbo where they can revert to an earlier energetic state? While this may seem speculative, some physicists propose that black holes, neutron stars, and other extreme remnants may operate under principles that bridge quantum mechanics and general relativity, domains of physics that remain deeply incompatible in current theories. Another possible explanation involves exotic forms of matter. Beyond neutron stars and black holes, theoretical models predict the existence of even more extreme states of matter, such as quark stars or strange stars. Unlike typical stellar remnants, these objects may not collapse completely but instead stabilize in a bizarre in-between state. If some zombie stars are actually failed black holes or quark-based remnants, their unique structures could allow them to intermittently flare up as their internal compositions shift. In other words, these objects might not be experiencing true resurrection but rather long periods of dormancy interrupted by occasional energy releases. The role of magnetism in these stars' apparent rebirths also cannot be ignored. Some neutron stars, particularly Magnetars, possess magnetic fields trillions of times stronger than Earth's. These fields can generate intense bursts of radiation, sometimes powerful enough to be observed across interstellar distances. If zombie stars have similar magnetic properties, their intermittent flares could be the result of magnetic instabilities, where stored energy is periodically released in violent bursts. This might explain why some stars appear to come back to life multiple times. Perhaps their magnetic fields undergo cycles of accumulation and discharge, mimicking the process of reignition. But what if zombie stars are not anomalies at all, but rather key pieces in a much larger cosmic puzzle? If these objects are able to temporarily restart fusion, even in small amounts, it could mean that the life cycles of stars are far more dynamic than we currently assume. What if, instead of stars simply burning out and fading away, there are mechanisms that allow them to periodically regain activity under the right conditions? If so, could there be stars that never truly die, but instead persist indefinitely, oscillating between active and dormant phases for billions or even trillions of years? This idea aligns with some alternative models of stellar evolution that suggest that certain remnants, particularly white dwarfs, may undergo long-term fluctuations in brightness due to unknown feedback mechanisms. Instead of cooling into inert black dwarfs, some white dwarfs could be reigniting on timescales too vast for human observation. If this were the case, then zombie stars might not be unique but instead an underappreciated stage of stellar life that only appears rare because we lack the ability to observe long enough timeframes. A radical possibility is that some of these stars may be interacting with dark matter or dark energy in ways that we have yet to understand. If dark matter is composed of exotic particles capable of weak interactions with ordinary matter, then under extreme conditions, such as in a stellar remnant's dense gravitational field, these interactions could trigger bursts of energy. In this scenario, zombie stars might not be reigniting in the traditional sense, but rather momentarily converting dark matter into detectable radiation. This would make them indirect probes into one of the most elusive and mysterious components of the cosmos. Even more mind-boggling is the idea that these stars could be remnants of previous cosmic epochs. If the universe is cyclic, undergoing phases of expansion and contraction over trillions of years, then zombie stars might not be ordinary objects from our own universe but instead survivors of a previous iteration of reality. If certain types of stellar remnants can persist across cosmic rebirths, they could act as ancient witnesses to multiple versions of the cosmos, flickering back to life when conditions allow. Ultimately, the study of zombie stars forces us to confront the limits of our understanding of physics. They challenge our assumptions about how energy behaves, how entropy progresses, and whether death, at least on a cosmic scale, is ever truly permanent. If stars can resist their own destruction, even briefly, then what else in the universe might be capable of similar defiance? Could entire galaxies experience cycles of rebirth? Could black holes, long thought to be one-way doors to oblivion, someday erupt back into existence in ways we cannot yet imagine? Zombie stars are more than just anomalies. They are cosmic paradoxes that defy categorization. They remind us that the universe is still full of surprises, that our models of physics are still evolving, and that even the most fundamental principles, such as the inevitability of stellar death, may have exceptions. As we continue to explore these objects, we may uncover new laws of nature that reshape our entire view of reality. What if zombie stars are not the exception but the rule? What if we have been looking at the universe all wrong, assuming finality where none exists? And what if, by understanding these strange celestial bodies, we come one step closer to understanding the deepest mysteries of existence itself? If zombie stars hint at a deeper, more intricate reality, then their existence challenges one of the fundamental principles of the cosmos, that once energy is exhausted, systems should decay irreversibly. Yet here we are, witnessing the impossible, stars that should have died reigniting against all expectations. This defiance of thermodynamic inevitability raises profound questions, not only about stellar evolution but also about the very nature of time, energy, and the limits of physical laws. One of the most intriguing possibilities is that these stars are tapping into some hidden reservoir of energy, something beyond traditional fusion or thermonuclear reactions. Could there be a universal force, as yet undiscovered, that allows certain objects to momentarily suspend their decay? If so, where does this energy come from? Some theories suggest that extreme gravitational environments, like those found in the dense cores of dead stars, could facilitate exotic quantum interactions that momentarily allow energy to resurface in ways we don't yet understand. Consider the concept of vacuum energy, a property of empty space itself. According to quantum field theory, even the vacuum isn't truly empty. It teems with fluctuations of energy at microscopic scales. While these fluctuations are normally too small to be observed directly, could they somehow play a role in zombie stars' strange behavior? If certain stellar remnants interact with this underlying quantum field, could they extract bursts of energy that allow them to flicker back to life? This idea isn't as far-fetched as it seems. The Casimir effect, a well-documented quantum phenomenon, demonstrates that vacuum energy can exert measurable forces on physical objects. If a dying star collapses into a dense, exotic state, its extreme gravitational environment might amplify vacuum fluctuations in ways we haven't yet predicted, causing unexpected outbursts of radiation. In this scenario, zombie stars wouldn't be defying physics. They would be revealing a deeper layer of physics that we have yet to fully comprehend. Another possibility is that zombie stars are not operating in isolation but are instead influenced by unseen cosmic forces. Could these stellar remnants be interacting with higher dimensional structures that momentarily inject energy back into their decaying forms? Theoretical physics suggests that our universe might be just one of many, and some models propose that energy could transfer between parallel realities under specific conditions. If zombie stars are, in some way, leaking energy from other dimensions, then their flickering resurrections could be evidence of a hidden multiversal connection. Even within the framework of traditional astrophysics, the mechanisms behind zombie stars raise intriguing paradoxes. If some stars can reignite, even briefly, does this mean that stellar death is not as final as we once thought? Could there be other classes of stars, ones that don't fit into the traditional models of white dwarfs, neutron stars, or black holes, that persist in an in-between state, either fully alive nor fully dead? Some astronomers have speculated that the study of zombie stars could lead to the discovery of entirely new stellar classifications. What if certain high-mass stars evolve in ways that allow them to undergo repeated cycles of collapse and rebirth, their interiors generating enough pressure to restart nuclear fusion intermittently? If such stars exist, they could represent a missing link in our understanding of how the most extreme objects in the universe behave over long timescales. Another striking implication of zombie stars is their potential connection to black holes. While black holes are typically thought of as the final stage of a star's collapse, some physicists propose that not all collapsing stars inevitably become singularities. Instead, under certain conditions, a stellar core might hover at the brink of black hole formation without fully crossing the event horizon. These so-called quasi-black holes could retain the ability to emit energy in bursts, perhaps explaining some of the irregular rebrightening events seen in zombie stars. Could zombie stars be failed black holes? If so, this could provide an entirely new avenue for studying gravity at its most extreme limits. Black hole formation is still not fully understood, and if some objects exist on the threshold between neutron stars and full-fledged singularities, their study could help us unravel the most mysterious aspects of general relativity. Yet another theory suggests that zombie stars could be relics from an earlier era of the universe. If some stellar objects formed under conditions different from those of today, they might possess unusual properties that allow them to behave in unexpected ways. For instance, in the early universe, matter was far more densely packed, and the laws governing particle interactions may have been subtly different. If certain stars have persisted since those primordial epochs, they might still exhibit characteristics that no longer exist in modern stellar evolution. This raises the tantalizing question: could zombie stars be among the oldest objects in the cosmos? If they are, then their study could provide a unique window into the physical conditions that existed billions of years ago, when the universe was still young. They might serve as cosmic fossils, holding clues about the formation of the first galaxies and the fundamental forces that shaped the universe in its infancy. At an even grander scale, zombie stars challenge our notions of cosmic finality. If death is not absolute for stars, then what about for galaxies? Could entire galaxies undergo similar cycles of decay and renewal? Some astronomers have already speculated that certain regions of space appear to switch on and off over long timescales, their active galactic nuclei flaring and fading unpredictably. If the principles governing zombie stars apply on a larger scale, then the universe itself might be more dynamic than we ever imagined. And what about black holes? If energy can resurface in dead stars, could the same principle apply to the singularities at the centers of galaxies? Some radical theories suggest that black holes might not be eternal prisons of matter, but instead temporary states in a much longer cosmic cycle. If so, could they eventually die in a way that mirrors the mysterious resurrections of zombie stars? Zombie stars are not just an astrophysical curiosity. They are a puzzle piece in a much larger mystery, one that may redefine how we think about matter, energy, and even the nature of reality itself. The fact that some stars refuse to die suggests that the cosmos is not a simple, one-way progression toward entropy. Instead, it hints at a universe that is far more flexible, far more resilient, and perhaps even far more alive than we ever suspected. If we can unlock the secrets of zombie stars, we might not only change our understanding of stellar physics, we might change our understanding of existence itself. Are we witnessing a fundamental loophole in the laws of thermodynamics? Have we stumbled upon a new category of celestial objects that operate under rules we have yet to define? Or are these flickering stars just the beginning, the first glimpses of a hidden mechanism that governs the life and death of everything in the universe? The mystery remains unsolved, but one thing is clear: the universe is far stranger than we ever imagined. And as long as there are stars that refuse to die, the questions will only keep growing. If zombie stars exist as proof that stellar death is not always permanent, then what does this mean for our broader understanding of astrophysics? Could the same principles that allow these stars to reignite also apply to other cosmic structures, such as planets, galaxies, or even the universe itself? The implications stretch far beyond individual stars. This phenomenon might hint at an entirely new framework for how energy and matter interact across cosmic time. One of the most profound questions raised by zombie stars is whether their survival is a result of an external influence, or an intrinsic property of certain stars. Are these objects unique due to their individual composition, or are they responding to forces beyond our current understanding? The possibility that zombie stars could be influenced by interactions with dark matter or dark energy is particularly fascinating. Dark matter is one of the great unsolved mysteries of astrophysics, making up the vast majority of matter in the universe while remaining undetectable except through its gravitational effects. Could it play a role in the resurrection of certain stars? If zombie stars somehow interact with dark matter differently than normal stars, this might provide crucial evidence that dark matter is more than just a passive gravitational influence. Some theories suggest that dark matter could accumulate in the cores of dying stars, providing an unexpected energy source that allows them to temporarily reignite. Alternatively, dark energy, the mysterious force responsible for the accelerated expansion of the universe, might play a role in these stellar revivals. If dark energy has localized effects on certain objects, then it could act as a kind of cosmic fuel, briefly re-energizing stellar remnants before they fade once more. This would be a revolutionary discovery, as it would suggest that dark energy is not just a large-scale phenomenon, but something that can affect individual objects in measurable ways. Another compelling possibility is that zombie stars are linked to unknown quantum effects that become prominent under extreme conditions. In standard quantum mechanics, energy states are usually stable or follow predictable decay patterns. However, in the extreme environments of collapsing stars, quantum effects could behave in ways we don't yet fully understand. If quantum tunneling or exotic particle interactions are at play, they might provide an unexpected energy source that temporarily revives these stars. Some researchers have even proposed that zombie stars could be connected to hypothetical particles known as axions. Axions are theorized to be extremely light particles that could account for dark matter, and under certain conditions, they might convert into photons in the presence of strong magnetic fields. If axions exist, then a dense, collapsed star with an intense magnetic field could serve as a natural particle accelerator, converting axions into bursts of visible light that mimic a partial resurrection. Beyond physics, the idea of zombie stars has profound implications for how we perceive the universe's life cycle. Traditionally, cosmology has followed a model where the universe began with the Big Bang, evolves over billions of years, and will eventually succumb to entropy. But if some stars are capable of defying their own deaths, then perhaps the fate of the universe is not as predetermined as we once thought. Could there be a mechanism by which entire galaxies, or even the universe itself, undergoes cycles of decay and rebirth? Some cosmologists have suggested that the universe might experience big bounce scenarios, where it collapses and re-expands repeatedly rather than ending in a heat death. If stars can experience miniature versions of this, reigniting after their supposed demise, then they could be microcosmic representations of a much larger cosmic pattern. The very existence of zombie stars might hint at a fundamental property of the universe, that nothing truly dies, but rather transforms and reemerges in ways we are only beginning to understand. These possibilities push us into the realm of deep existential questions. If stars, which we consider to be the simplest forms of astronomical bodies, are capable of resurrection, then how does this principle apply to more complex systems? Could this concept of renewal extend beyond the stars to planets, galaxies, or even life itself? If the cycle of death and rebirth is a fundamental feature of the universe, then perhaps nothing ever truly ceases to exist. Rather, it simply transitions into a new form, waiting for the right conditions to emerge again. There is also the tantalizing possibility that zombie stars could be related to unknown forms of matter that exist beyond our current classification. In modern astrophysics, we recognize ordinary matter, and dark energy as the three primary components of the cosmos. But what if there is another form of matter, something that interacts with normal matter only under extreme conditions, such as those found in the remnants of dying stars? This unknown substance might be the missing link that explains how and why certain stars can reanimate long after they should have burned out. If zombie stars do not fit neatly into existing stellar models, then we may need to rewrite some of the fundamental principles of astrophysics. Could it be that our understanding of stellar life cycles is incomplete? While we have successfully modeled how stars form, burn, and die, these models are based on observations of normal stars. Zombie stars challenge that framework, suggesting that there may be hidden factors influencing stellar behavior that we have yet to identify. One possibility is that some stars possess an undiscovered internal mechanism that allows them to store and release energy in a way that is not accounted for in standard astrophysical models. If this is the case, then zombie stars might represent an entirely new class of celestial objects, ones that do not follow the simple pattern of life, death, and collapse, but instead exist in a state of fluctuating activity. This would mean that the universe is home to more diverse and unpredictable processes than we ever imagined. Astronomers continue to search for more examples of zombie stars, hoping that future observations will provide the key to unlocking their mysteries. Advanced telescopes, such as the James Webb Space Telescope, are capable of detecting faint and distant stellar objects with unprecedented clarity. If we can identify more cases of zombie stars, we may be able to piece together a pattern that explains their bizarre behavior. But even if we solve the mystery of zombie stars, the questions they raise will remain. What other cosmic phenomena exist that we have yet to discover? If stars can refuse to die, what else in the universe might be capable of similar feats? Could we one day find entire systems or galaxies that have experienced partial rebirths? And if the universe itself operates under a principle of renewal, then what does this mean for the ultimate fate of everything that exists? Zombie stars are more than just an anomaly. They are a sign that the universe is far more complex, and far more mysterious, than we ever imagined. Their very existence forces us to rethink the nature of time, energy, and death itself. They suggest that the cosmos is not a place of simple endings, but of endless cycles, where even the most impossible resurrections are possible. As our understanding deepens, one thing becomes clear: we are only scratching the surface of the mysteries that the universe holds. And as long as zombie stars continue to flicker back to life, they will remind us that in the vast, unfathomable depths of space, even the most fundamental laws can sometimes be rewritten. The presence of zombie stars challenges one of the fundamental principles of astrophysics, that a supernova marks the absolute end of a star's life cycle. Traditionally, when a massive star exhausts its nuclear fuel, it collapses under its own gravity, leading to a supernova explosion. This explosion either leaves behind a dense neutron star or a black hole, or it completely disperses the star's material into space. But zombie stars refuse to follow this script. They erupt in catastrophic explosions, only to inexplicably reignite, as if some unknown mechanism allows them to resurrect from the ashes of their own destruction. What makes these resurrections even more baffling is that they do not conform to a single pattern. Some zombie stars reignite shortly after their supposed death, while others remain dormant for extended periods before suddenly bursting back to life. The inconsistency of these revivals suggests that there may be multiple processes at play, some internal to the star itself and others driven by external cosmic forces. One hypothesis is that zombie stars are the result of a special type of thermonuclear reaction that allows residual material in the stellar core to reignite under extreme conditions. In this scenario, a dying star might not fully detonate in its first explosion. Instead, a dense core remains, surrounded by debris and still burning outer layers. If enough material falls back onto this remnant core, it could trigger a secondary fusion event, creating a new outburst of energy that gives the appearance of resurrection. However, not all zombie stars fit this explanation. Some of these stars have been observed to undergo multiple cycles of explosion and revival, which suggests that their behavior is not simply a one-time anomaly but an ongoing process. This raises a deeper question: what allows certain stars to escape the finality of death while others succumb permanently? One of the most fascinating aspects of zombie stars is their connection to pulsational parinstability supernovae. These supernovae occur when extremely massive stars experience runaway nuclear reactions due to the formation of electron-positron pairs in their cores. Instead of collapsing directly into a black hole, these stars undergo repeated explosive outbursts, shedding layers of material while maintaining a central core. Over time, they can experience multiple violent eruptions before eventually stabilizing, or, in some cases, reigniting in full-force supernovae. If pulsational parinstability supernovae play a role in the zombie star phenomenon, then these objects may represent an intermediate stage between supernovae and long-term stellar remnants. This would mean that zombie stars are not truly defying physics, but rather existing in a unique, previously unrecognized category of stellar evolution. Another intriguing possibility is that zombie stars owe their rebirth to interactions with a companion star. In binary systems, two stars orbit around a shared center of mass, often exchanging material over time. If a white dwarf or neutron star is locked in a close orbit with a companion, it can gradually siphon material from its partner. This influx of fresh fuel can reignite nuclear fusion, temporarily reviving the dead star and causing it to shine once more. This process is observed in some types of recurrent novae, where a white dwarf accumulates hydrogen from a neighboring star until it reaches critical mass and undergoes a thermonuclear detonation. But zombie stars exhibit more extreme behavior than typical novae, suggesting that something more complex is occurring, perhaps a delayed detonation or an unexpected mechanism that allows the remnant core to sustain fusion far longer than expected. Could there be a connection between zombie stars and the strange behavior of magnetars? Magnetars are neutron stars with extraordinarily strong magnetic fields, thousands of times more powerful than those of ordinary neutron stars. These magnetic fields can cause sudden, high-energy bursts of radiation, sometimes years after the neutron star was formed. If some zombie stars are actually extreme versions of magnetars, then their periodic reignitions could be the result of magnetic instabilities releasing stored energy in sudden bursts. But what if zombie stars are not just strange remnants of ordinary stars? What if they represent an entirely new type of celestial object, something that exists on the fringes of known physics? Some researchers have speculated that zombie stars might be linked to exotic matter or even unknown forms of energy. One radical hypothesis is that zombie stars might interact with hypothetical mirror matter, a proposed counterpart to normal matter that does not interact via electromagnetic forces, making it nearly invisible. If mirror matter exists and occasionally mixes with normal matter under extreme conditions, then it could act as an unexpected energy source, allowing a dead star to reignite. Another possibility is that zombie stars hint at unknown aspects of quantum physics. In classical physics, energy dissipation follows predictable rules, but in the quantum realm, particles can tunnel through barriers, spontaneously appear and disappear, and behave in ways that defy intuition. If quantum effects influence the energy states of collapsed stars in ways we do not yet understand, then the seemingly impossible resurrection of these objects might be an indication that our current models of physics are incomplete. The discovery of zombie stars also raises profound philosophical and cosmological questions. If death is not always final for stars, then how universal is the principle of entropy, the idea that systems tend toward disorder and decay? Could the universe itself possess mechanisms for rejuvenation that we have yet to recognize? Some cosmologists have suggested that the universe might be cyclic, with periods of collapse and rebirth rather than a single irreversible trajectory toward heat death. If zombie stars demonstrate that individual objects can experience multiple life cycles, then they might provide an observational clue that the universe itself follows a similar pattern on a grander scale. This brings us to one of the most mind-bending possibilities, that zombie stars might be linked to phenomena beyond our own universe. If our cosmos is part of a larger multiverse, then interactions between different universes could create anomalies that appear to defy physics as we understand it. Could zombie stars be manifestations of energy transfers between different cosmic domains? If so, then their existence might hint at a deeper, hidden structure of reality itself. Astronomers continue to search the skies for more examples of zombie stars, hoping that future discoveries will provide definitive answers. The next generation of space telescopes, such as the Vera C. Rubin Observatory, promises to provide unprecedented insights into transient cosmic events, allowing scientists to detect and analyze these enigmatic objects in greater detail than ever before. But even as our understanding advances, the mystery of zombie stars reminds us that the universe is still full of surprises. For every question answered, new mysteries arise. And in the depths of space, where stars refuse to die, we are reminded that even the most fundamental laws of physics may not be as immutable as we once believed. Perhaps zombie stars are a testament to the resilience of the cosmos, a reminder that even in the darkest moments, light can still find a way to shine again. The enigma of zombie stars not only challenges our understanding of stellar evolution, but also forces astrophysicists to reconsider the very nature of energy conservation and matter distribution in extreme cosmic environments. Every known principle of thermodynamics suggests that once a star has exhausted its fuel and undergone a supernova, there should be no viable mechanism for it to reignite on its own. And yet, observational evidence confirms that some stars defy this finality, illuminating the cosmos once more despite their apparent demise. One of the most striking examples of a potential zombie star is IPTF-14HLS, a star that erupted in a supernova event yet continued to brighten and dim over several years, a behavior that completely contradicts our current models of how supernovae function. Normally, when a star explodes, the resulting supernova releases an immense amount of energy in a short time, then fades away as the ejected material cools and expands into space. But IPTF-14HLS exhibited repeated bursts of luminosity, as if the explosion never fully finished or kept reigniting for reasons unknown. Scientists first detected this bizarre object in 2014, but when they traced its past observations, they found something even more astonishing. The same star had apparently exploded in 1954, decades before its 2014 event. How could the same star undergo two supernovae separated by more than half a century? The most immediate assumption was that astronomers had made a mistake, that these were simply two different objects. However, spectral analysis confirmed that the light signatures matched, indicating that this was indeed the same celestial body experiencing multiple cycles of destruction and revival. One theory suggests that IPTF-14HLS and similar objects might be examples of failed supernovae, explosions that do not fully disrupt the star but instead leave behind a dense core capable of reigniting under the right conditions. In this scenario, the explosion ejects a large amount of outer material but fails to destroy the star's central mass completely. If enough energy remains trapped within the core, it could restart fusion reactions, leading to repeated outbursts that make it appear as though the star is coming back to life. Another possibility is that these stars are engaging in an unusual process of matter recycling. In most supernovae, the expelled material disperses irreversibly into space. But what if, under certain conditions, some of this ejected mass could be reabsorbed by the remaining stellar core? If a zombie star exists in a dense region of space, surrounded by its own previously expelled matter, gravitational forces might allow it to reclaim lost material and use it as fresh fuel for renewed nuclear reactions. This could explain the periodic rebrightening observed in objects like IPTF-14HLS. Each new ignition cycle could be the result of the star accumulating enough recycled matter to reignite fusion, leading to another mini-explosion that mimics a supernova. Such a process, if confirmed, would revolutionize our understanding of stellar death, suggesting that in some cases, supernovae might not be true endpoints, but rather phases in a more complex cycle of collapse, reaccumulation, and rebirth. Complicating matters further is the fact that not all zombie stars exhibit the same behavior. Some, like IPTF-14HLS, show multiple explosive outbursts over extended periods. Others appear to blink, in and out of visibility, disappearing for years or even decades before suddenly flaring up again. This raises the question of whether we are dealing with a single phenomenon or multiple distinct processes that all lead to similar observational results. One speculative hypothesis suggests that some zombie stars could be undergoing a kind of stellar hibernation. If a star has just enough energy to maintain a low level of activity but not enough to sustain full-fledged fusion, it might enter a state of dormancy. In this state, nuclear reactions would be minimal, keeping the star just barely above the threshold of visibility. Then, if external forces, such as gravitational interactions with nearby objects, disrupt this equilibrium, the star could suddenly reawaken, producing a burst of energy that makes it appear as though it has returned from the dead. This idea ties into another intriguing possibility, that zombie stars might interact with exotic astrophysical objects such as black holes or neutron stars. If a zombie star exists in a binary system with a compact object, then the tidal forces exerted by its companion could strip away layers of material at periodic intervals. This stripped material could temporarily suppress the star's brightness, making it seem as though the star had disappeared. But when enough material is drawn back or reprocessed by the surviving stellar core, the star could flare up again, creating the illusion of resurrection. Even more astonishing is the possibility that zombie stars might be tied to processes occurring at the quantum level. Some physicists speculate that under extreme conditions, matter within the core of a dead star could enter a state of quantum degeneracy, where pressure from nuclear interactions temporarily halts collapse. In this state, strange quantum effects, such as particle-antiparticle interactions or vacuum fluctuations, could generate bursts of energy large enough to restart nuclear fusion, if only for brief periods. If this hypothesis is correct, it could suggest that zombie stars are more than just astrophysical anomalies. They could be experimental grounds for observing exotic physics in action. By studying these objects in greater detail, scientists might uncover new laws governing high-energy states of matter, or even gain insights into the fundamental structure of spacetime itself. The implications of zombie stars extend far beyond astrophysics. If stars can defy death and reignite in unexpected ways, then what does that say about the universe as a whole? Could there be other celestial phenomena operating on similarly mysterious cycles of destruction and rebirth? Some researchers have drawn parallels between zombie stars and the theoretical concept of cosmic rebirth, in which the universe itself undergoes cycles of collapse and renewal over unimaginable timescales. This concept, sometimes referred to as the Phoenix universe hypothesis, suggests that rather than expanding indefinitely or collapsing into a singularity, the cosmos might oscillate between periods of expansion and contraction, much like a zombie star undergoing cycles of death and revival. If such a process is possible on the stellar scale, then perhaps similar mechanisms exist at even grander levels of reality. As telescopes and observational techniques continue to improve, astronomers will likely uncover more examples of zombie stars, potentially providing clearer explanations for their baffling behavior. Future missions, such as those planned for the James Webb Space Telescope and the upcoming generation of space observatories, may offer direct insights into the internal mechanics of these celestial anomalies. But for now, zombie stars remain one of the most perplexing and awe-inspiring mysteries of the cosmos. They challenge everything we thought we knew about stellar life cycles, defy the apparent finality of supernovae, and hint at hidden forces that may be reshaping our understanding of the universe itself. Perhaps, in studying these undead stars, we are glimpsing a deeper truth, one that reveals the cosmos as a place not of simple endings, but of endless transformations and unexpected resurrections. If zombie stars truly exist in larger numbers than we currently suspect, it raises profound questions about how many stars we have mistakenly assumed to be dead. Could there be entire populations of these undead stars scattered across the universe, hiding among the remnants of supernovae, waiting for the right conditions to reignite? If so, it would force us to reconsider the very nature of what it means for a star to die. The traditional model of stellar evolution presents a linear path. A star forms, burns its fuel, and ultimately meets its end, whether by fading into a white dwarf, collapsing into a black hole, or exploding in a supernova. But zombie stars introduce an element of unpredictability into this sequence, suggesting that for some stars, death may not be a singular, irreversible event, but rather a complex, cyclical process. One of the most important implications of these findings is the potential impact on our understanding of supernovae themselves. If some stars can survive multiple explosive events, then our existing classifications of Type I, Type II, and other supernova types may need to be revised. It suggests that some supernovae we observe might not be final explosions at all, but rather intermediary stages in a longer, more drawn-out process of stellar evolution. This could also have implications for the measurement of cosmic distances, since Type I supernovae are often used as standard candles to determine distances across the universe. If some of these explosions come from zombie stars rather than completely destroyed stars, it could introduce new variables that astronomers must account for. Another major question surrounding zombie stars is what role they might play in galactic ecosystems. In the conventional model of stellar death, supernovae contribute to the enrichment of galaxies by dispersing heavy elements into space, fueling the formation of new stars and planets. But if some stars are able to reignite, does this process occur in a different way? Could zombie stars act as reservoirs for certain elements, delaying their release into space until some later, unknown event forces them to fully disintegrate? Or could they contribute to the formation of unusual stellar objects that do not fit into our current classifications? One possibility is that zombie stars could serve as progenitors for exotic compact objects, such as Magnetars or unusual neutron star configurations that we have yet to fully understand. A magnetar, for instance, is an extremely dense neutron star with an unimaginably powerful magnetic field, so strong that it can warp the structure of atoms themselves. If a zombie star undergoes repeated cycles of explosion and reignition, it might eventually collapse into a magnetar instead of a more typical neutron star, creating an object with properties that differ from anything previously observed. Some researchers have even suggested that zombie stars could be linked to hypernovae or long-duration gamma-ray bursts, phenomena that involve far more energy than a typical supernova. If a zombie star continues to accrete matter and reignite over time, it might eventually build up enough instability to produce an explosion of unprecedented scale. This could help explain some of the most energetic cosmic events we have detected, which otherwise seem to defy the known limits of stellar explosions. Observational evidence for zombie stars remains limited but compelling. Beyond IPTF-14HLS, other candidates have been identified, though none with quite the same dramatic history. Some stars have been observed flaring up unexpectedly, appearing to experience bursts of energy long after they should have faded. Others have exhibited puzzling variability in their light curves, suggesting that they may be undergoing intermittent periods of renewed fusion. However, the full nature of these objects remains uncertain, and further study is needed to confirm whether they represent true zombie stars or some other unknown astrophysical phenomenon. One approach to solving this mystery is through continuous long-term monitoring of known supernova remnants. If some of these remnants show signs of unexpected rebrightening, it could provide valuable clues about how zombie stars operate. Space telescopes such as the James Webb Space Telescope, along with ground-based observatories equipped with cutting-edge imaging technology, are likely to play a key role in uncovering more evidence. Theoretical models also need to be refined. While several hypotheses have been proposed to explain zombie stars, none have been conclusively proven. More advanced simulations of stellar evolution, incorporating factors such as unusual nuclear processes or interactions with external material, could help determine the conditions under which a star might survive multiple supernovae. If we can better understand the physics at play, it may even be possible to predict which stars have the potential to become zombies before they explode. Ultimately, the discovery of zombie stars serves as a powerful reminder that the universe is far more complex than our current models suggest. Just as dark matter and dark energy have forced astronomers to rethink fundamental aspects of cosmology, so too might zombie stars require a reevaluation of what we thought we knew about stellar death. If stars can rise from the ashes of their own destruction, then what other surprises might the cosmos have in store for us? The study of zombie stars is still in its early stages, and much remains to be learned. But one thing is clear: these celestial anomalies challenge our assumptions about the life cycle of stars and hint at new, undiscovered physics that could reshape our understanding of the universe. As we continue to probe deeper into the mysteries of space, we may find that zombie stars are not an isolated oddity, but rather a crucial piece of a much larger cosmic puzzle, one that could ultimately reveal secrets about the very nature of existence itself. If zombie stars are more common than we currently realize, their existence could have profound implications for astrophysics, including our understanding of cosmic evolution, nuclear physics, and even the ultimate fate of stars across the universe. The idea that some stars can seemingly escape their inevitable destruction and continue to shine raises a fundamental question: how many stars have we prematurely classified as dead, when, in reality, they are merely in a dormant state, waiting for the right conditions to reignite? If these objects turn out to be a natural and frequent part of stellar evolution, then many of our long-held assumptions about the life cycle of stars may need to be revised. One of the biggest puzzles surrounding zombie stars is their energy source. In a traditional supernova explosion, the core collapses, and the outer layers are violently ejected into space, leaving behind either a neutron star or a black hole. The energy output is so immense that it marks the definitive end of the star's fusion process. But for zombie stars like IPTF14HLS, this finality does not seem to apply. Instead, they somehow reignite and continue to shine, sometimes for years after their initial explosion. This suggests that either the core does not fully collapse as expected, or that some external mechanism, such as an influx of fresh hydrogen or an unusual nuclear reaction, allows them to persist far longer than normal. One leading theory suggests that these stars may be undergoing a process similar to what is known as the pulsational pair instability phenomenon. This occurs in extremely massive stars when the intense radiation pressure in their cores creates electron-positron pairs, reducing the outward pressure that normally counteracts gravity. This leads to a series of partial explosions, where the star ejects layers of its outer material but does not fully collapse. If a star enters this state, it could theoretically survive multiple rounds of explosions, appearing to die and then come back to life repeatedly. Another possibility is that these stars are not undergoing traditional nuclear fusion at all, but are instead being powered by some exotic process, such as interaction with a binary companion. In some cases, a nearby star could donate material to the zombie star, triggering a renewed burst of energy. This could explain why some zombie stars flicker back to life sporadically rather than continuously, as they may be experiencing intermittent periods of mass transfer. One particularly intriguing idea is that zombie stars may be influenced by the presence of dark matter. If certain types of dark matter particles interact with normal matter in ways we do not yet understand, they could theoretically provide an additional source of energy, allowing a star to continue burning long after it should have collapsed. Some researchers have even speculated that dense clumps of dark matter may be capable of accumulating within dying stars, preventing them from fully collapsing and instead allowing them to enter a strange, undead state. Observationally, detecting more zombie stars is challenging, as most supernovae fade away after their initial explosion, leaving little trace of their former existence. However, if we expand our search criteria to include objects that appear to reignite unexpectedly, we may uncover more examples of this phenomenon. Long-term monitoring programs, such as those conducted by the Vera C. Rubin Observatory, could be instrumental in identifying stars that display unusual variability following a supernova event. Another approach involves analyzing archival data from past supernovae to see if any of them exhibited unexpected signs of continued activity. If researchers can find multiple cases similar to IPTF14HLS, it would suggest that zombie stars are not a one-time anomaly, but rather a recurring feature of the cosmos. The implications of these findings could extend far beyond individual stars. If zombie stars contribute to multiple supernova-like explosions over time, they could play a previously unrecognized role in distributing heavy elements throughout the universe. The periodic ejection of material from these stars could enrich surrounding interstellar space in a way that differs from conventional supernovae, potentially affecting star and planet formation in ways we do not yet fully understand. Furthermore, if zombie stars can exist for centuries or longer, it raises the possibility that some of the stars we currently observe as normal may in fact be living on borrowed time, merely waiting for the next explosion to occur. This could mean that some stellar objects we have classified as particularly luminous or massive are actually in the midst of a drawn-out, multi-stage death process, rather than being stable stars in their prime. There is also the tantalizing possibility that some of these stars could eventually collapse into black holes in ways we have not previously considered. If a zombie star continues to undergo repeated outbursts but retains enough mass, it could eventually reach a critical point where it can no longer stave off gravitational collapse. However, instead of collapsing in a single, dramatic event, it may do so in stages, leading to a slow, gradual transformation into a black hole over time. This could help explain some of the mysterious intermediate mass black holes that astronomers have struggled to account for. If zombie stars can transition into black holes through a process of repeated explosions and partial collapses, it could provide a missing link between stellar mass black holes and the more massive ones found at the centers of galaxies. As research into zombie stars continues, astronomers will need to refine their models of stellar evolution to accommodate this unexpected phenomenon. New computational simulations may be required to determine under what conditions a star can enter this cycle of repeated explosions, and whether certain factors, such as metallicity, mass, or environment, make some stars more likely to become zombies than others. Ultimately, the discovery of zombie stars challenges our most fundamental assumptions about the life cycle of stars. For decades, we have believed that the end of a star's life is marked by either a slow fade into obscurity, or a cataclysmic explosion that leaves nothing behind but a compact remnant. But zombie stars suggest that, in some cases, death is not the end. Instead, some stars may find ways to resist their fate, clinging to life through mechanisms we have only begun to understand. What does this tell us about the universe? Perhaps it serves as a reminder that even in the harshest and most unforgiving environments, survival is possible. The cosmos is full of surprises, and just when we think we have unraveled its mysteries, it presents us with new questions that force us to rethink everything we thought we knew. Zombie stars are one such mystery, a phenomenon that defies our expectations and invites us to look deeper into the nature of stellar death and rebirth. As technology advances and our ability to observe the universe improves, it is likely that we will uncover even more bizarre and unexpected phenomena that challenge our understanding of physics. Zombie stars may just be the beginning. What other strange and unexplainable objects might be lurking in the depths of space, waiting to be discovered? The answer to that question may redefine our knowledge of the cosmos and, perhaps, even our place within it. If zombie stars are merely the beginning of a broader category of resurrected cosmic objects, then we may be on the verge of a new understanding of how the universe recycles itself. The implications stretch far beyond just stellar evolution, into the formation of elements, the structure of galaxies, and even the nature of space and time itself. If some stars refuse to die, what other celestial objects might possess hidden mechanisms of persistence, resisting the entropy-driven fate we have long assumed is inevitable? One of the more radical ideas emerging from the study of zombie stars is the possibility that their survival is linked to unknown physics. The conventional framework of astrophysics states that once a supernova occurs, the star's core collapses, and its remaining energy is either locked inside a neutron star, dispersed into space, or, in extreme cases, concentrated into a black hole. But zombie stars defy this expectation, suggesting that some process, perhaps an exotic form of matter, a novel type of fusion, or even a gravitational effect we do not yet understand, allows them to reignite. Some researchers speculate that highly magnetized environments might play a role in sustaining these stars. Magnetars, for instance, are neutron stars with extremely strong magnetic fields that can generate bursts of energy millions of times more powerful than the sun's entire output. If a dying star had an unusually strong magnetic field, could it temporarily prevent a full collapse, allowing it to exist in an undead state? The interplay between magnetic forces and nuclear fusion is still not entirely understood, and it is possible that this relationship holds some of the answers to the mystery of zombie stars. Another possibility is that the energy driving zombie stars comes from an external source. Some astronomers propose that interstellar gas clouds might be feeding these stars, supplying them with the necessary fuel to sustain nuclear fusion. If a star undergoes a supernova but then drifts into a dense region of gas, it could theoretically absorb enough material to briefly restart fusion before dying out again. This would create a pulsating effect, where the star appears to wake up periodically as it absorbs new fuel before fading once more. If this is true, then it raises an even more profound question: could other objects in space, including planets or even failed stars like brown dwarfs, experience similar revival effects under the right conditions? Could entire planetary systems that we assume to be dead actually be reactivated in some unknown way? This possibility extends the mystery beyond individual stars, hinting at a broader cosmic cycle of death and rebirth that we have yet to fully grasp. One of the most exciting aspects of studying zombie stars is that they challenge the limits of our technology and observational techniques. Traditional telescopes look for patterns in light, heat, and radiation, but zombie stars may not behave in predictable ways. They might appear normal for decades before suddenly flaring up, meaning that astronomers must rely on long-term observation projects to catch these rare events in action. Future telescopes, such as the James Webb Space Telescope and next-generation radio observatories, may be able to detect zombie stars by identifying unusual spectral signatures. If these stars undergo repeated supernova-like outbursts, they should leave behind unique chemical fingerprints in the surrounding space. By analyzing these signatures, astronomers may be able to pinpoint stars that have experienced multiple explosive events, offering new insights into their life cycle. Beyond observation, theoretical physicists are working to develop new models that account for the existence of zombie stars. These models must reconcile the apparent contradictions between established stellar evolution theories and the strange reality presented by these undead stars. If current physics cannot explain them, then the discovery of zombie stars may force a re-evaluation of the fundamental forces that govern the universe. Some researchers have even suggested that these stars could be linked to the mysterious process of quantum gravity, the elusive theory that seeks to unify general relativity with quantum mechanics. If zombie stars exist in a strange, intermediate state between life and death, they might offer clues about how matter behaves at extreme energy densities, potentially shedding light on the nature of black holes and even the origins of the universe itself. Another possible connection lies with white holes, a theoretical counterpart to black holes that expel matter instead of absorbing it. Some theories propose that, under certain conditions, a dying star could transition into a white hole-like state, ejecting energy and material instead of collapsing into a singularity. If zombie stars operate on a similar principle, they could represent an entirely new phase of stellar evolution, one in which stars do not merely collapse or fade away but instead oscillate between explosive outbursts and quiet dormancy. The study of zombie stars may also have unexpected implications for our understanding of time itself. If these stars can exist in a suspended state for centuries or longer before suddenly reactivating, then it suggests that stellar death is not necessarily a linear process. Instead of a simple beginning, middle, and end, some stars may experience long, unpredictable cycles of destruction and rebirth. This could mean that time, at least on a cosmic scale, operates in ways we do not fully understand. If time behaves differently near these strange stars, could they provide hints about the deeper structure of reality? Some physicists speculate that certain cosmic objects may be able to skip across time due to extreme gravitational or energetic conditions. If zombie stars exist in a kind of time-dilated state, where they experience supernovae and bursts separated by what, to an outside observer, appear to be centuries, then they could offer clues about how time itself is shaped by the universe's most violent events. Ultimately, the discovery of zombie stars forces us to confront one of the most fundamental questions in astrophysics. Is anything in the universe truly dead? If stars can seemingly rise from the grave, then what does that mean for our assumptions about cosmic finality? Could other objects, perhaps even entire galaxies, harbor hidden layers of existence, waiting to be uncovered? In the coming decades, as our ability to study the universe improves, it is likely that we will find more zombie stars and perhaps even stranger cosmic phenomena that challenge our understanding of life and death on an astronomical scale. Each new discovery pushes the boundaries of human knowledge, reminding us that the cosmos is far more complex and mysterious than we have ever imagined. Perhaps the most profound realization to come from the study of zombie stars is that the universe itself is not a static, predictable machine but a dynamic, ever-changing entity filled with surprises. The more we look, the more we find that the universe does not always follow the rules we expect. Instead, it constantly reinvents itself, presenting us with puzzles that force us to rethink everything we thought we knew. Zombie stars are just one piece of this cosmic puzzle. But they may be among the most important, because they challenge us to confront the limits of our understanding and push beyond them. In doing so, they remind us that the universe is alive in ways we are only beginning to comprehend. And if some stars refuse to die, what else might we have underestimated about the nature of existence itself? If zombie stars refuse to die, it raises a profound question. Is stellar death truly permanent, or is it just another phase in a more complex cycle of cosmic rebirth? The existence of these undead stars forces us to reconsider not just the end stages of stellar evolution, but also the very nature of energy, matter, and time in the universe. If a star can explode and yet somehow reignite, what else might be capable of defying its expected fate? One of the most fascinating aspects of zombie stars is how they challenge our understanding of nuclear fusion. In a normal star, fusion occurs when immense gravitational pressure forces hydrogen atoms to merge into helium, releasing energy that counteracts the star's tendency to collapse under its own weight. This delicate balance continues for millions or even billions of years until the fuel runs out, at which point the star either fades into a white dwarf or explodes in a supernova. However, zombie stars appear to break this rule. If a star has already gone supernova, then by all logic, its fusion process should have ceased permanently. Yet, these stars seem to reignite, producing bursts of energy that should not be possible given their prior destruction. Some scientists propose that this resurrection could be driven by the accumulation of new material from space. If a dead star drifts through a dense region of gas and dust, it might accrete enough mass to reignite fusion in a process known as delayed nuclear burning. This is similar to how white dwarfs and binary systems can siphon material from their companion stars until they reach a critical mass and explode in a type I supernova. However, in the case of zombie stars, there is no clear evidence of an external donor supplying them with fuel. Instead, they appear to regenerate energy from within, as if something inside them refuses to extinguish completely. Could there be a hidden source of energy sustaining these stars long after their supposed demise? One possibility is that exotic forms of matter, such as strange quark matter or axion-like particles, could be at play. Some physicists believe that when a star collapses, it might form an inner core composed of strange quark matter, an ultra-dense state of matter that could theoretically remain stable for long periods, occasionally releasing bursts of energy as it transitions between different states. If zombie stars contain such exotic matter, they might be able to intermittently flare up without requiring traditional nuclear fusion. Another theory suggests that some of these stars may be interacting with dark matter, one of the universe's biggest mysteries. Dark matter is believed to make up around 85% of the total mass of the universe, yet it does not interact with light or normal matter in any conventional way. If certain stars reside in regions with unusually high concentrations of dark matter, they might absorb this mysterious substance in a way that triggers brief periods of energy release. This would explain why some zombie stars appear to flicker back to life for short durations before fading again, as if they are feeding on an unknown cosmic fuel source. Even more speculative is the idea that zombie stars could be linked to quantum effects at a macroscopic scale. In quantum mechanics, particles can exist in superposition, meaning they can be in multiple states at once until they are observed. While this phenomenon is usually confined to the microscopic world, some researchers wonder if extreme environments like supernova remnants could exhibit similar effects on a stellar scale. If zombie stars exist in a state of quantum flux, they might occasionally jump between energy states in ways that defy classical physics. This would make them one of the few known macroscopic objects to demonstrate quantum behavior, offering a potential bridge between the laws of quantum mechanics and general relativity. The mystery deepens when considering the timeframes involved. Some zombie stars appear to reignite mere decades after their supposed death, while others show signs of activity centuries or even millennia later. This suggests that whatever process is driving their rebirth is not uniform. It can manifest on vastly different timescales depending on the conditions of each star. Could this imply that there are many more zombie stars scattered throughout the universe, lying dormant for thousands or even millions of years before suddenly flaring back to life? If so, the true number of these undead celestial bodies could be far greater than we currently realize. This possibility challenges the way astronomers have traditionally classified stellar remnants. Up until now, it was assumed that when a star reaches its final stage, Whether as a white dwarf, neutron star, or black hole, its fate is sealed. But the existence of zombie stars suggests that some of these remnants may exist in a liminal state, fluctuating between activity and dormancy in ways that defy our current models. If the boundaries between life and death are not as clear-cut as we once thought, what other cosmic phenomena might exhibit similarly unpredictable behavior? One potential clue could come from pulsars, highly magnetized neutron stars that emit beams of radiation as they spin. Pulsars are known for their incredible precision, with some acting like cosmic lighthouses that flash on and off at exact intervals. However, astronomers have occasionally observed pulsars that seem to glitch, suddenly changing their rotation speed or even disappearing from view before reappearing later. Could some pulsars be linked to the same mechanisms that drive zombie stars? If so, studying these anomalies might provide further insight into the forces at work. Similarly, astronomers have detected mysterious fast radio bursts, FRBs, brief, powerful signals originating from deep space that defy explanation. Some of these bursts appear to repeat at irregular intervals, suggesting that they might be linked to objects undergoing cyclical periods of activity and dormancy. While some FRBs have been traced to Magnetars, others remain completely unexplained. Could zombie stars be a source of some of these enigmatic signals? If so, it would mean that their sporadic reanimation is not just a local phenomenon but one that can be detected across vast cosmic distances. The more we investigate, the more it seems that the universe is filled with strange, self-renewing phenomena that refuse to fit within our established theories. The existence of zombie stars is not just an odd curiosity, it is a fundamental challenge to our understanding of how matter and energy behave on cosmic scales. If stars can return from the brink of death, then it suggests that even the most violent and catastrophic processes in the universe may not be as final as we once believed. This realization could have profound implications for other areas of astrophysics. For example, what if black holes, which we currently view as the ultimate endpoint of stellar collapse, also possess some hidden mechanism that allows them to re-emerge in new forms? Could there be unknown processes at work that allow these cosmic objects to recycle themselves in ways we have yet to detect? If so, it would mean that the cycle of cosmic life and death is far more dynamic than we ever imagined. Ultimately, the mystery of zombie stars reminds us that the universe is still filled with unknowns. Despite centuries of scientific progress, we are constantly discovering new phenomena that challenge our assumptions and force us to expand our understanding of reality. These undead stars serve as a testament to the fact that nature often refuses to follow the rules we expect, and that the cosmos is still capable of surprising us in the most unexpected ways. As our technology advances and our ability to observe the universe improves, it is likely that we will uncover even more examples of celestial objects defying death. Whether through new observational techniques, deeper theoretical insights, or even direct detection of the unknown forces at play, the enigma of zombie stars is one that promises to reshape our understanding of the cosmos. For now, they remain one of the greatest unsolved mysteries of space, a phenomenon that challenges the very definition of what it means for a star to truly die. If zombie stars exist, then perhaps death in the universe is not as absolute as we once thought. Could there be other cosmic objects that undergo similar resurrections? Could entire galaxies or even planets experience forms of renewal that we have yet to understand? The existence of zombie stars raises countless questions, each more profound than the last. One of the most compelling aspects of these stars is that they do not follow a single, uniform pattern. Some appear to flicker back to life in a matter of decades, while others remain dormant for centuries or even longer before suddenly reigniting. This suggests that there are multiple pathways by which a star can become undead, each governed by unique physical mechanisms. But what exactly allows them to break free from the constraints of stellar evolution? Some astronomers believe that highly magnetized neutron stars, known as Magnetars, could play a role in these mysterious rebirths. Magnetars possess the most intense magnetic fields in the known universe, trillions of times stronger than Earth's, and their energy output can be staggeringly high. If a stellar remnant interacts with a magnetar's magnetic field, it could potentially trigger a burst of energy powerful enough to temporarily reanimate it. This could explain why some zombie stars exhibit flashes of brightness at seemingly random intervals. Another possibility is that some supernova remnants contain highly unstable elements that continue to undergo nuclear reactions long after the explosion. Traditional supernova theory assumes that once the outer layers of a star are ejected, all fusion ceases. However, some evidence suggests that certain exotic isotopes might persist in a semi-active state, slowly releasing energy over time. If these isotopes suddenly experience a phase transition or an external trigger, such as a collision with interstellar material, they could briefly reignite, giving the illusion that the star has come back to life. One of the strangest cases of a zombie star is IPTF-14HLS, a supernova that exploded multiple times over several years. This event completely defied expectations, as a normal supernova should be a one-time event, expelling its outer layers in a single, cataclysmic explosion before fading away. Yet IPTF-14HLS continued to brighten and dim repeatedly, as if it refused to die. This has led some scientists to speculate that it may have been powered by a process we do not yet understand, perhaps even an entirely new form of stellar nuclear reaction. Could zombie stars be remnants of an ancient cosmic cycle? Some theories suggest that certain stars might not merely explode but instead undergo partial collapses, retaining enough mass to reignite later. This idea challenges the very foundations of how we classify supernovae. It raises the question of whether the universe contains a hidden class of stars that do not fit into our current models, objects that exist in a liminal state, either fully alive nor fully dead. Even more intriguing is the potential link between zombie stars and black holes. If a supernova fails to completely destroy its progenitor star, could the remnants become trapped in a gravitational feedback loop, oscillating between collapse and expansion? Some models suggest that if a dying star has just the right conditions, particularly in terms of angular momentum and mass distribution, it might form a temporary event horizon that later dissipates, allowing it to re-emerge as a star-like object. This would effectively make zombie stars a missing link between neutron stars and black holes, further blurring the line between these cosmic end states. And what about dark matter? Could zombie stars interact with this invisible substance in ways that allow them to reignite? If dark matter has properties beyond what we currently assume, it could act as an energy source for dying stars, fueling brief but powerful bursts of renewed activity. Some researchers believe that if dark matter particles can interact weakly with normal matter, they might accumulate within stellar remnants, eventually reaching a critical threshold that triggers energy release. This could also explain why zombie stars appear in unexpected locations. If dark matter is not evenly distributed across the universe, but instead clumps together in certain regions, then we would expect to see these mysterious stars appearing where dark matter densities are highest. This theory is still speculative, but it could provide an entirely new perspective on how dark matter influences the visible universe. If zombie stars are more common than we think, then it is possible that we have been misinterpreting other astronomical phenomena for decades. Could some of the objects classified as variable stars actually be remnants of exploded stars that are intermittently reigniting? Could some of the unexplained high-energy emissions detected in distant galaxies be linked to these resurrected stellar corpses? The deeper we look into space, the more we find that the universe is filled with anomalies that refuse to fit into our existing theories. From pulsars that glitch unpredictably to stars that explode multiple times, it seems that the cosmos operates on rules far stranger than we ever imagined. Zombie stars are not just an isolated curiosity. They are a clue that something fundamental about our understanding of stellar death is incomplete. If stars can defy death, what else might be possible? Could entire planetary systems survive the destruction of their parent stars in ways we have not yet considered? Could black holes themselves undergo transformations that allow them to temporarily re-emit light? The existence of zombie stars forces us to entertain possibilities that were once dismissed as science fiction. And yet, despite the growing body of evidence that these objects exist, we are still no closer to fully understanding how they work. Are they the product of unknown physical processes, or do they hint at entirely new branches of physics that we have yet to discover? Are they rare cosmic anomalies, Or are they far more common than we currently realize? The only certainty is that our current models of stellar evolution are incomplete, and that the universe still holds secrets that defy explanation. With each new telescope and each new observation, we move closer to unlocking these cosmic mysteries. Perhaps the next great discovery in astrophysics will come not from searching for new stars, but from studying those that refuse to die. The undead stars of the universe are a reminder that in space, even destruction is not always the end. The story of these resurrected celestial bodies is still being written, and until we unravel the full truth behind their existence, they will remain one of the greatest enigmas of the cosmos. The mystery of zombie stars is not just a curiosity, it is a direct challenge to our understanding of physics. Every accepted model of stellar evolution suggests that a supernova marks the definitive end of a star's life. The explosion disperses the star's outer layers into space, leaving behind either a neutron star, a black hole, or, in some cases, nothing at all. The fact that we have observed stars that somehow continue burning, sometimes for years or even decades after their supposed deaths, forces us to reconsider whether our theories about stellar death are complete. Could it be that some stars never truly die? Or do they go through cycles of death and rebirth that we have yet to fully understand? To truly appreciate how shocking zombie stars are, we must first understand what happens during a normal supernova. When a massive star exhausts its nuclear fuel, the delicate balance between the inward pull of gravity and the outward push of radiation collapses. The core of the star contracts rapidly, triggering either a violent explosion or a direct collapse into a black hole. In the case of a Type II supernova, the explosion is triggered when the core collapses to such an extreme density that it rebounds, sending shock waves through the outer layers. This process releases more energy in a few seconds than our Sun will emit in its entire 10 billion year lifetime. After a supernova, what remains depends on the mass of the original star. If the core is between about 1.4 and 2.3 times the mass of the Sun, it forms a neutron star, a city-sized remnant made almost entirely of neutrons, supported against further collapse by quantum mechanical forces. If the core is more massive, it collapses into a black hole, a region of spacetime where gravity is so intense that not even light can escape. Either way, the star is dead, at least, according to conventional astrophysics. And yet, reality appears to be much more complex. Astronomers have observed multiple instances of supernovae that seem to defy these expectations. Some stars explode, fade away, and then inexplicably brighten again. Others remain visible for much longer than they should, suggesting that some unknown process is keeping them alive. These stars, dubbed zombie stars, are unlike anything we ever expected to see. One of the most famous examples is IPTF-14HLS, a supernova that was first detected in 2014 but later found to have actually exploded back in 1954. Instead of fading within a few months, as expected, it continued to shine for years. Even more puzzling, it experienced multiple peaks in brightness, as if it were repeatedly undergoing new explosions. This was unprecedented. Supernovae are supposed to be one-time events, cataclysmic outbursts that signal the end of a star's life. Yet IPTF-14HLS refused to die. The existence of such a star suggests that either we are missing key details about how supernovae work, or that entirely new physical processes are at play. One possibility is that the star somehow managed to hold onto a portion of its hydrogen envelope, allowing it to experience repeated nuclear flashes rather than a single catastrophic explosion. Another theory suggests that the supernova was triggered by a process known as parent stability, in which gamma rays within the star's core produce electron-positron pairs that alter the balance of pressure and gravity. This could lead to a series of pulsations and explosions over a long period, explaining the multiple outbursts. Yet another possibility is that some zombie stars might be interacting with unseen companions. In binary systems, a dying star can sometimes siphon material from its partner, temporarily reigniting nuclear fusion in its outer layers. This could create the illusion that the star has come back to life when, in reality, it is simply borrowing mass from its neighbor. If the donor star continues supplying material, the process could repeat indefinitely, leading to multiple brightening events over time. Some researchers have even speculated that zombie stars could be powered by dark matter. If certain types of dark matter particles can interact with normal matter in exotic ways, they might be capable of supplying enough energy to sustain nuclear reactions in a dying star. While this idea is highly speculative, it could help explain why some zombie stars appear to shine far longer than expected. But perhaps the strangest possibility is that zombie stars could be linked to black holes in ways we do not yet understand. Some models suggest that if a star's core collapses into a black hole but retains some of its outer layers, those layers might continue orbiting the black hole, occasionally igniting as they fall inward. This could create periodic bursts of energy, making the star appear to flicker back to life. In this scenario, the star would be both dead and alive at the same time, an astronomical paradox that challenges everything we know about stellar death. There is also the question of whether zombie stars might be connected to other unexplained cosmic phenomena. Some astrophysicists have drawn comparisons between these mysterious stars and fast radio bursts, FRBs, brief but powerful bursts of radio waves that appear to originate from distant galaxies. While most FRBs last only milliseconds, a few have been observed repeating over time. Could these signals be linked to the strange activity of zombie stars? If so, they might represent an entirely new way for dying stars to release energy, one that has remained hidden from us until now. The deeper we look, the more questions arise. Could some stars experience multiple deaths over the course of their lifetimes? Could certain types of stellar remnants oscillate between states of activity and dormancy? And if so, what does this mean for the broader life cycle of stars? If even death is not always permanent, then we may need to rethink the entire history of the universe. Zombie stars are not just an anomaly, they are a warning that we do not yet understand the full complexity of stellar evolution. Every time we believe we have reached the limits of our knowledge, the universe finds a way to prove us wrong. What other surprises might be waiting for us among the stars? Could there be other celestial objects that defy death in even more extreme ways? Until we unravel the secrets of these undead stars, we can only wonder at the true extent of the universe's mysteries. And so, the hunt for zombie stars continues. With new telescopes and advanced observation techniques, astronomers are constantly scanning the cosmos, searching for more evidence of these impossible stars. Each new discovery brings us closer to understanding their true nature, but for now, they remain one of the greatest unsolved puzzles in astrophysics. Perhaps, one day, we will uncover the full truth behind their existence. Until then, they will continue to haunt the universe, flickering in the darkness, refusing to fade away. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.